Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're setting out on a very unusual kind of journey. Not towards something bright or explosive or full of stars, but towards something much quieter, much emptier. In fact, we're heading toward one of the largest known regions of almost nothing in the entire universe. A place so vast, so strangely empty, that even galaxies seem to have forgotten to show up. It's called the Boater's Void, and despite its rather friendly-sounding name, it might just be one of the most unsettling places we've ever discovered. Now, before we gently drift into that emptiness, let me ask you something simple. Where in the world are you listening from right now? And perhaps just as fitting for tonight's topic, what time is it where you are? Maybe it's late evening and the day is slowly winding down. Or maybe it's the quiet hours of the night when everything feels a little softer, a little more distant. Wherever you are, you're here, in your own small corner of the universe, while we talk about a place where there are almost no corners at all. If you find this kind of slow exploration soothing, or just a pleasant way to let your mind wander while your body rests, feel free to give the video a like or subscribe. It helps this quiet little space reach others who might need a calm moment too. Now settle in, let your thoughts slow down a little, and imagine this with me. Picture the night sky. Not as it looks from your window, perhaps with a few stars peeking through, but as it really is when you step far enough away from Earth. A vast dark canvas, scattered with galaxies like distant islands of light. Each galaxy is enormous in its own right. Billions, sometimes trillions of stars, all held together by gravity drifting through space like glowing cities. And yet, even between those galaxies there is space, a lot of it. More than we usually think about. If you were to zoom out farther and farther, you'd start to see that galaxies aren't evenly spread out. They gather together in clusters and filaments, forming something scientists call the cosmic web. Long strands of matter stretching across the universe, with enormous gaps in between. Those gaps are called voids. Already that might sound a bit unsettling. Regions of space where there are fewer galaxies, less matter, more emptiness. But even among those voids, the Boater's Void stands out, because it isn't just a little empty, it's profoundly empty. The kind of empty that makes even astronomers pause for a moment and say, "That's strange." To begin understanding just how strange, it helps to think about how we normally expect the universe to behave. After the Big Bang, matter didn't spread out perfectly evenly. Tiny differences in density, barely noticeable at first, grew over time. Gravity pulled matter together into clumps. Those clumps became stars, galaxies, clusters of galaxies. Over billions of years, this process created structure, patterns, a kind of cosmic architecture. So when scientists map the universe, they don't see randomness. They see filaments, walls, clusters, and in between them, voids that are relatively empty, but still not completely devoid of matter. That's the key part. Relatively empty. Even the emptiest regions usually contain some galaxies, a few lonely ones scattered here and there, enough to remind you that the universe is still present, even in its quietest corners. But the Boater's Void behaves a little differently. It's not just a gap between structures, it's more like a vast bubble where almost nothing formed at all. And when we say vast, we don't mean in the casual sense of the word. We mean something that stretches the limits of imagination. But we'll get to the size soon enough. For now, let's stay with the feeling of it. Imagine you're travelling through space, not in a hurry, just drifting. You pass one galaxy, then another far in the distance, then clusters, where galaxies gather like glowing cities in the dark. Then, gradually, they begin to thin out. The distances between them grow larger, the light becomes more sparse, and eventually you reach a point where you look around and realise there's almost nothing left. No nearby galaxies, no clusters, just a faint scattering of distant light, so far away it barely feels real. You've entered the Buddha's void. What's fascinating is that we didn't always know this place existed. For a long time, astronomers assumed that on large scales the universe was fairly uniform, not perfectly even, but not wildly uneven either. Then, in the early 1980s, something unexpected appeared in the data. Astronomers mapping the distribution of galaxies noticed a huge region where galaxies were almost entirely absent. At first, it seemed like a mistake. Maybe the data was incomplete. Maybe the instruments had missed something. But as observations improved, the pattern remained. There really was a massive region of space with far fewer galaxies than expected. And not just a little fewer, dramatically fewer. It was like looking at a map of a bustling city and finding an entire district where almost no buildings had been constructed. Naturally, this raised questions. Was it just a statistical fluke? A rare but possible outcome of how matter clumps together? Or was something deeper going on? Over time, more detailed surveys confirmed that the Buddha's void was real, and it was enormous. But what made it truly intriguing wasn't just its size, it was the contrast. Because just outside the void, the universe looks normal. Galaxies form structures, clusters, filaments. Everything behaves as expected. Then suddenly, there's this vast region where that structure almost disappears. It's a bit like walking through a forest, surrounded by trees, and then stepping into a clearing so large you can't see the edges. At some point, your brain starts to question whether you're still in the same forest at all. That's the kind of shift the Buddha's void represents. And yet, despite how empty it isn't completely devoid of matter. There are a few galaxies inside it, just a handful, compared to what we'd expect in a region of that size. These galaxies are often described as some of the loneliest in the universe, not because they're physically different, but because of where they are. Imagine being a galaxy surrounded by almost nothing. No nearby neighbours, no clusters to interact with, no dense environment shaping your evolution, just vast distances in every direction. In a way, they're like isolated islands in an ocean so large that even the horizon feels distant. And this raises another interesting thought. If you were inside the Buddha's void, what would the universe look like? From Earth, we see a sky filled with stars, and beyond them, galaxies in every direction. But from deep within the void, the view would be very different. The nearest galaxies would be incredibly far away. The sky would feel darker, emptier. The sense of being part of a vast, interconnected cosmic structure would fade. Instead, you might feel like you are floating in a kind of cosmic solitude. Now, whether that solitude feels peaceful or unsettling probably depends on your perspective. Some might find it calming, a kind of ultimate quiet. Others might find it deeply disorienting, because we're used to thinking of the universe as something full of stars, galaxies, light. The Buddha's void reminds us that, on the larger scales, emptiness plays just as big a role, and perhaps even more so. As we continue, we'll start to explore just how large this emptiness really is, and why it challenges our intuition so strongly. Because saying something is big in space doesn't quite capture it. Not really. We'll need better comparisons, better ways to picture it, and maybe along the way, a slightly different way of thinking about size itself. But for now, just stay with the idea. A region of space so vast, so quiet, that even galaxies seem rare, and somewhere, drifting within it, a few lonely islands of light, surrounded by distances that stretch far beyond anything we experience here on Earth. Something rather curious happened when astronomers first began mapping the universe in detail. Up until a certain point, the expectation was fairly simple. If you looked far enough in any direction, you would find galaxies. Maybe not evenly spaced, maybe not perfectly arranged, but present. Like scattered lights across a distant landscape, some closer, some farther, but always there. That assumption made sense. After all, everywhere we had looked before, galaxies appeared. Large ones, small ones, spirals, ellipticals, clusters of them gathered together, sometimes even interacting. The universe, at least from our perspective, seemed full. Not crowded exactly, but populated. So when astronomers in the late 20th century began creating more detailed three-dimensional maps of galaxy positions, they expected to see that same general pattern repeated on larger scales, a kind of cosmic consistency. And at first, that's exactly what appeared. Galaxies weren't randomly scattered. They formed patterns, long thread-like structures, often called filaments, stretched across space. Clusters gathered where these filaments intersected, like cities at the crossroads of cosmic highways. It was already a fascinating discovery. The universe wasn't just a random spread of matter, it had structure, a kind of architecture. But then, in the middle of all that structure, something unexpected showed up, or rather didn't show up. As astronomers plotted galaxy positions, they noticed regions where galaxies were strangely scarce. At first, these appeared as small gaps. Nothing too surprising. After all, even in a structured universe, you'd expect some areas to be less dense than others. But as the maps expanded, one particular region began to stand out. It wasn't just a small gap. It was enormous, and it was quiet. The region lay in the direction of the constellation Boötes, a patch of sky that, from Earth, looks no different than any other. Just another arrangement of distant stars, familiar shapes traced by human imagination. But when astronomers looked beyond those stars into the deeper universe, they found something unsettling. There were far fewer galaxies than expected. Not just slightly fewer, dramatically fewer. To understand how strange that is, imagine you're mapping out a large city at night, marking every building that has lights on. Most areas show a steady pattern. Some neighbourhoods are brighter, some dimmer, but overall the lights are there. Then, suddenly, you come across a region where the lights almost vanish. Not completely gone, but reduced to just a few scattered points. Your first instinct might be to check your equipment. Maybe something's wrong with the data. Maybe the observations were incomplete. Maybe clouds got in the way, or the instruments missed something. That's exactly what astronomers thought at first, because finding such a vast region with so few galaxies wasn't just unexpected. It was hard to believe, so they checked, and then they checked again. Different observations, different telescopes, different methods. The same pattern kept appearing. The emptiness was real. This was one of the first moments when the Boötes void revealed itself, not as a dramatic discovery with a single announcement, but as a quiet realization that something was missing. And in science, sometimes what's missing can be just as important as what's present. What made this discovery particularly interesting was the context in which it happened. By the early 1980s, astronomers were beginning to understand that the universe had large-scale structure. The idea of the cosmic web was emerging, with galaxies forming filaments and clusters separated by less dense regions. Voids, in general, were already part of that picture, but those voids were expected to be moderate in size. Large, yes, but not extreme. The Boötes void, on the other hand, didn't quite fit that expectation. It was too big, too empty. It wasn't just a gap between structures. It was more like an enormous bubble carved out of the cosmic web. And that raised an interesting question. How do you even notice something like that? After all, you can't directly see emptiness. You don't observe nothing in the same way you observe a star or a galaxy. Instead, you infer it. You map what is there, and then you notice where things are missing. It's a bit like drawing a picture by placing dots on a page. If you leave a large blank area in the middle, that blankness becomes part of the picture. In this case, astronomers were placing dots representing galaxies across a three-dimensional map of the universe, and the Boötes void appeared as a vast region where the dots simply stopped, or at least nearly stopped. There were a few galaxies inside, but so few that they felt almost accidental. like someone had scattered a handful of grains across an otherwise empty surface. One of the more interesting aspects of this discovery is how it changed the way scientists thought about the universe on large scales. Before, it was tempting to imagine that, given enough distance, everything would average out, that the universe would look roughly the same everywhere. But the Bota's void suggested that, even on enormous scales, there could be significant variations, regions where matter gathered densely, and regions where it almost didn't gather at all. That idea might sound familiar in a different context. If you've ever looked at foam, like the bubbles in a bath or the froth on top of a drink, you might notice that it isn't uniform. There are clusters of bubbles separated by thin walls with empty spaces in between. The universe, in a very loose sense, behaves a bit like that. Galaxies form along the walls and filaments, while voids occupy the spaces in between. But again, the Bota's void stands out, because if the universe is like foam, this void is like an unusually large bubble, one that makes you wonder why it formed that way. And perhaps more importantly, whether it's truly unusual or just one of many we haven't fully mapped yet. At the time of its discovery, it certainly felt unusual. It pushed the boundaries of what scientists expected, and as more data came in, the picture became clearer. The void wasn't a mistake. It wasn't a temporary illusion caused by incomplete observations. It was a genuine feature of the universe, a vast region where galaxy formation had been significantly suppressed. Now, that leads to another subtle but important point. The Bota's void isn't empty in the absolute sense. There's still matter there. Dark matter, gas, a few galaxies. But compared to the surrounding regions, it's extremely underdense. And that difference is what makes it so striking. It's not the absence of everything. It's the absence of almost everything, which in a universe that tends to fill space with structure is quite remarkable. As astronomers continued to study this region, they began to refine their measurements. They mapped its boundaries more precisely. They counted the galaxies within it. They compared it to other voids, and gradually a clearer picture emerged. The Bota's void was not only real, but it was one of the largest known voids of its kind, a kind of cosmic outlier. And with that realization came a shift in perspective. Instead of asking, "Is this real?" scientists began asking, "How did this happen? Why would such a large region of space end up so empty? Was it simply a statistical fluctuation, an extreme but natural outcome of how matter clumps together? Or was there something about this region that made it evolve differently?" Those questions would lead to deeper investigations into the nature of cosmic structure, dark matter, and the early universe. But before we get there, it's worth pausing for a moment and just appreciating the discovery itself. Because there's something quietly fascinating about the idea that, in the vastness of the universe, one of the most significant findings came from noticing an absence. Not a bright explosion, not a new kind of star, but a region where, for reasons not yet fully understood, galaxies simply didn't gather. It's a reminder that the universe isn't just defined by what we see, it's also shaped by what we don't, and sometimes the quietest places can tell the most interesting stories. At this point, it might help to slow things down just a little and gently ask a very simple question. What exactly is the Bota's void? Because so far we've described it as empty, vast, unusual. But those words, while accurate, are also a bit slippery. They give you a feeling but not quite a clear picture. So let's bring it into focus. The Bota's void is what astronomers call a cosmic void. That's the technical term for a region of space where there are far fewer galaxies than average. Now that might sound straightforward, but it helps to understand the context. If you could zoom far enough out and look at the universe on its largest scales, you wouldn't see galaxies spread evenly like dots on a page. Instead, you'd see something more like a network. Galaxies gather along long, thin filaments, forming vast structures that stretch across hundreds of millions of light years. Where these filaments intersect, you get clusters, dense regions filled with galaxies, and in between those filaments there are gaps. Those gaps are voids. So in that sense, voids are not unusual. They're actually a normal part of how the universe is organized. But here's where things get interesting. Most voids are, in a way, gently empty. They still contain galaxies, just fewer of them. If you were to travel through a typical void, you'd still occasionally pass by a galaxy or two. The distances would be larger, the space quieter, but not completely silent. The Bhuta's void is different. It's not just a low-density region, it's an extreme low-density region. To get a sense of that, imagine you're expecting a certain number of galaxies in a given volume of space. Based on the average density of the universe, you might predict hundreds, maybe thousands, depending on the size. Inside the Bhuta's void you find only a handful, not zero, but so few that each one feels almost like an exception rather than the rule. And that's what makes it so striking. It's not just that it's empty, it's that it's unexpectedly empty. Now let's talk about where it is. The Bhuta's void lies in the direction of the constellation Botas, which is visible from Earth's night sky. If you've ever looked up and seen the bright star Arcturus, you've already looked toward that region. Of course, the constellation itself is just a pattern of nearby stars within our own galaxy. The void is much, much farther away. We're talking hundreds of millions of light years. That means the light we receive from the galaxies around the void has been travelling toward us for hundreds of millions of years, long before humans existed, long before dinosaurs even. So when we map the Bhuta's void, we're not just looking at space, we're looking into the deep past. And what we see there is a region that, even back then, was already unusually empty. That detail is important, because it tells us that the void isn't something that formed recently. It's been there for a very long time, evolving along with the rest of the universe. Now, let's try to picture its shape. It's often described as roughly spherical, like a giant bubble. Not a perfect sphere, of course. The universe rarely deals in perfect shapes, but close enough that the analogy works. A vast three-dimensional region where matter density drops significantly compared to its surroundings. And surrounding that bubble, you find the usual structures. Filaments of galaxies, clusters, walls of matter forming the edges of the void. It's almost like the universe built a kind of boundary around it. Not a solid wall, but a region where galaxies are much more common. And inside that boundary, things become quiet. Very quiet. Now here's something subtle but important. When we say void, it's easy to imagine absolute emptiness. A perfect vacuum with nothing in it at all, but that's not quite the case. Even inside the Bhuta's void there is still matter. There's dark matter, which we can't see directly but can detect through its gravitational effects. There's diffuse gas spread thinly across the region. And there are those few galaxies we mentioned earlier, so it's not empty in the absolute sense. It's more like extremely underfilled, if the rest of the universe is like a loaf of bread with a fairly even distribution of air pockets. The Bhuta's void is like a giant bubble where the dough barely formed at all. And that comparison, while imperfect, helps highlight something important. The void isn't separate from the universe. It's part of the same structure. It follows the same physical laws. It just represents an extreme case of how those laws can play out. Another way to think about it is through contrast. If you take a region of space just outside the void, you'll find galaxies arranged in familiar patterns, clusters, filaments, interactions between galaxies. Then, as you move inward, those patterns begin to fade. The distances between galaxies increase. The interactions become rarer. The overall density drops, until eventually you're in a region where galaxies are so sparse that they no longer define the structure in any meaningful way. And that transition is part of what makes the Bhuta's void so fascinating. It's not just a static region, it's part of a larger system, a boundary between something and almost nothing. Now you might wonder how astronomers actually define something like this. After all, space doesn't come with labels or clear borders. There's no sign that says, "You're now entering the void." Instead, scientists use statistical definitions. They look at the average density of galaxies in the universe, and then they identify regions where the density drops below a certain threshold. If a region is significantly underdense compared to the average, it can be classified as a void. The Butter's void isn't just slightly below that threshold, it's far below it, which is why it stands out so clearly in galaxy surveys. When you map the positions of galaxies in 3 dimensions, it appears as a large dark region, surrounded by brighter, denser areas, almost like a hole in the cosmic web. And that image, while simple, is quite powerful, because it reminds us that the universe isn't just made of matter, it's also shaped by the absence of matter. The spaces between structures are just as important as the structures themselves. They influence how galaxies move, how gravity pulls, how the universe evolves over time. In fact, voids like the Butter's void are thought to expand over time. As matter is pulled into denser regions, the underdense regions become even emptier. They grow, slowly, gently, over billions of years. So the Butter's void we observe today may actually be larger than it was in the past, a kind of expanding bubble of emptiness, shaped by the same gravitational forces that build galaxies elsewhere. And that brings us back to the central idea. The Butter's void is not just a place, it's a feature of how the universe organizes itself. A region where the usual process of structure formation didn't proceed as strongly as it did elsewhere, where matter didn't clump together as efficiently, where galaxies, for reasons we're still exploring, remained few and far between. And in that sense, it's not just empty, it's informative. It tells us something about the early universe, about how matter moved, about how tiny differences in density can grow into enormous differences over time. But perhaps more than anything, it challenges our intuition. Because when we think of the universe, we tend to think of it as full of stars, galaxies, light. The Butter's void reminds us that, on the larger scales, emptiness is just as fundamental. That vast regions of space can exist where almost nothing happens, and yet, those regions are still part of the same grand story. Up to this point, we've been talking about emptiness, structure, and the idea of a vast region where galaxies are surprisingly scarce. That already feels unusual, maybe even a bit unsettling. But there's another layer to this that quietly changes everything. Size. Because when astronomers describe something as large, especially in the universe, they're not using the word casually. They're describing distances so extreme that our usual ways of thinking don't quite hold up. So let's slow this down and ask the question gently. Just how big is the Butter's void? The short answer is this. It spans roughly 330 million light-years across. Now, that number might sound impressive, but also a bit abstract. Million light-years is one of those phrases that feels large, but doesn't always translate into something we can truly picture. So instead of rushing past it, let's unpack it carefully. A light-year is the distance that light travels in 1 year. And light, as you may know, moves incredibly fast. About 300,000 kilometers every second. In just 1 second, light can circle the Earth more than 7 times. In a single minute, it travels millions of kilometers. In a year, it covers nearly 9.5 trillion kilometers. So when we say 330 million light-years, we're talking about a distance so vast that even light, the fastest thing we know, would take 330 million years to cross it from one side to the other. Just pause on that for a moment. If a beam of light started travelling across the Butter's void back when the first dinosaurs were appearing on Earth, it still wouldn't have reached the other side until long after they had disappeared. That's the scale we're dealing with. And yet, even that comparison only scratches the surface, because our brains are quite good at compressing large numbers into something manageable. Millions of years starts to blur together after a while. So let's try a different approach. Think about our own galaxy, the Milky Way. It's enormous, about 100,000 light-years across, filled with hundreds of billions of stars. If you imagine travelling from one edge of the Milky Way to the other, even at the speed of light, it would take 100,000 years. That alone is already far beyond anything we experience in daily life. Now, take that galaxy, with all its stars, planets, and structure, and imagine placing it inside the Bhuta's void. You wouldn't just fit one Milky Way across it. You could line up thousands of Milky Ways from one side of the void to the other. Thousands! And not touching, not overlapping, but spaced out across that vast emptiness. That begins to give you a sense of the scale, but we can go a little further. Let's imagine something slightly more familiar. Picture Earth. Now imagine the distance between Earth and the Sun. That's about 150 million kilometers, a distance we call 1 astronomical unit. Light takes about 8 minutes to travel that distance. Now stretch that outward, past the outer planets, past the edge of our solar system, out into interstellar space. Eventually you reach the nearest star, Proxima Centauri, about 4.2 light years away. Already that feels far, but compared to the Bhuta's void, that distance is almost negligible. You would need to repeat that journey tens of millions of times to span the void, and even then you're only just beginning to grasp its size. Another way to think about it is through travel time. Let's say, purely hypothetically, that you had a spaceship capable of travelling at a very high speed. Not quite the speed of light, but something advanced enough to cross interstellar distances. Even then, crossing the Bhuta's void would take an extraordinary amount of time, hundreds of millions of years, longer than the entire existence of complex life on Earth, longer than the rise and fall of countless species, civilizations, and geological changes. In fact, by the time you reach the other side, Earth itself would likely look completely different. Continents shifted, climates changed, perhaps even entirely new forms of life, and that's just for crossing a single void. Now, here's something that makes this even more interesting. The Bhuta's void isn't just large in isolation. It exists within a universe that contains many such structures, though most are smaller. What makes this one special is that it's among the largest known, a kind of extreme example of how empty a region of space can become, and that raises a subtle but fascinating point. When we talk about size in the universe, we're not just talking about distance. We're also talking about scale relative to structure. A galaxy is large, but it's also dense with stars. A cluster of galaxies is larger, but still full of matter. The Bhuta's void, on the other hand, combines enormous size with extreme emptiness. It's not just big, it's big and quiet. And that combination is what makes it feel so difficult to grasp. Because when we imagine something large, we often imagine something filled. A vast ocean, a wide landscape, a crowded city. The Bhuta's void is more like an ocean with almost no water, a landscape with almost no features, a space where the usual markers of scale are missing. And without those markers, our sense of size becomes a bit unstable. There's another interesting way to approach this. Think about how we measure distances in everyday life. We rely on familiar reference points. A kilometre, a mile, the distance between cities. Even when we think about larger distances, like crossing a country or flying between continents, we still have context. We know what those journeys feel like. But in space, especially on this scale, those reference points disappear. There are no roads, no landmarks, no sense of progression in the way we're used to. Just vast distances, measured in light years, stretching far beyond direct experience. And that's why scientists often rely on comparisons, not because the numbers aren't precise, but because the numbers alone aren't enough. They need something to anchor them, something that connects the abstract to the imaginable, even if only slightly. So when we say the Bhuta's void is 330 million light-years across, what we're really saying is this. It's a region so large that light itself takes hundreds of millions of years to cross it. It could contain thousands of galaxies like our own, yet it mostly doesn't. It stretches far beyond anything we can physically travel, observe directly, or fully comprehend. And yet, it's just one feature among many in the universe. That last part is perhaps the most quietly surprising. Because as enormous as the Bhuta's void is, it's not unique in the sense of being the only large void. There are others, Smaller, yes, but still vast, which suggests that emptiness on this scale is not an exception. It's part of the pattern, a recurring feature of how the universe organizes itself. And that leads to an interesting shift in perspective. Instead of thinking of the universe as something mostly filled with matter, dotted with occasional empty regions, we begin to see it as something mostly empty, with matter gathered into structures within it. The voids aren't just gaps, they're a fundamental part of the whole. In a way, the Buddha's void is a reminder of that. A particularly striking example of how much space there really is between the things we usually focus on. Numbers can take us quite far. They give us precision, they give us scale, they give us a sense that we understand what we're looking at. 330 million light years, trillions of kilometers multiplied over unimaginable spans, thousands of galaxies that could fit across it. And yet, after a while, those numbers begin to soften, not because they're incorrect, but because the mind quietly gives up trying to hold on to them. So instead of adding more numbers, let's try something gentler. Let's try to picture the Buddha's void in a way that feels a little more tangible. Not perfectly accurate perhaps, but closer to something we can sit with. Imagine you're looking at a map of the universe, not a literal one with labels and borders, but a kind of three-dimensional map where every galaxy is marked as a tiny point of light. At first, it looks like a scattered field of stars, but as you step back, you begin to notice patterns. The points aren't random, they gather into lines, clusters, sheets. Some regions are dense, others more sparse. And then there are the gaps. Now imagine zooming in on one of those gaps. At first, it doesn't seem too unusual, just a slightly quieter region. But as you zoom further, the emptiness grows. The surrounding galaxies recede into the distance. The space between them stretches, until eventually you're looking at a region where the usual pattern almost disappears. That's the Buddha's void. But even that still feels a bit abstract, so let's try something else. Picture a vast, dark ocean at night. Not the kind you might see from a coastline, but one far from land, where the horizon stretches in every direction and there are no visible features. Now imagine that, instead of water, this ocean is space, and instead of waves, there are galaxies. In most parts of this ocean, you might occasionally see lights in the distance. Other ships, if you like, each one representing a galaxy. Some closer, some farther, but enough to remind you that you're not alone. But in the Buddha's void, those lights become incredibly rare. You might travel for what feels like an eternity without seeing anything at all. And when you finally do spot a distant light, it's so far away that it barely changes your sense of isolation. It doesn't feel like a busy ocean anymore. It feels like something else entirely. Now, let's shift the analogy slightly. Imagine a sponge, a large airy sponge with holes throughout it. The solid parts represent where galaxies gather, the filaments and clusters we talked about earlier. The holes represent the voids. Now take one of those holes and make it much larger than the others, not just slightly bigger, but dramatically so. That oversized cavity, surrounded by the sponge's structure, is a bit like the Buddha's void, except, of course, we're not dealing with something you can hold in your hand. We're dealing with a region so large that even light takes hundreds of millions of years to cross it. So the analogy works only up to a point. Still, it helps highlight something important. The void isn't separate from the rest of the universe. It's part of the same structure. It's defined by what surrounds it. Without the filaments and clusters, the void wouldn't stand out at all. It would just be everything. There's another way to approach this that leans more on experience than structure. Imagine you're standing in a familiar place, a city perhaps, or a forest. There are things around you, buildings, trees, sounds, movement. Even if it's quiet, there's still a sense of presence. Now imagine walking farther and farther away from everything. The buildings disappear, the sounds fade, the landscape becomes simpler, until eventually you're standing in a vast open desert, flat, empty, stretching in every direction. That already feels different. But now imagine that desert continuing, not for kilometres or even thousands of kilometres, but for distances so large that walking across it would take longer than the entire history of human civilization. And even then you haven't reached the edge. That begins to hint at what it might feel like to be inside something like the Bhutas void. But even that analogy falls short in one key way, because in a desert, you still have a ground beneath your feet, you still have a horizon, you still have a sense of up and down. In space, especially inside a void, those references disappear. There is no ground, no sky, no horizon in the usual sense, just directionless distance. And that changes the experience in a subtle but profound way. It's not just empty, it's disorientingly empty. Another interesting way to picture it is through time rather than space. Imagine sending a signal, a beam of light, from one side of the void to the other. Then imagine waiting, not for seconds or minutes, not even for years, but for hundreds of millions of years. Longer than the time it took for mammals to evolve, longer than the time since the dinosaurs disappeared, and only then does the signal reach the other side. That's the kind of distance we're dealing with. A distance that's almost easier to think of as time than as space, because in everyday life, distance and time are closely linked. We think of how long it takes to get somewhere, but in the Bhutas void, that connection becomes extreme. Travel and time blur together into something almost indistinguishable. There's also something interesting about how the mind reacts to emptiness on this scale. When we imagine something large but full, like a galaxy or a cluster, there's a sense of richness. There are details to focus on. Stars, colours, motion. Even if we can't see them all, we know they're there. But when we imagine something large and empty, the mind doesn't have as much to hold on to. It starts to drift, to fill in the gaps, or sometimes to leave them completely blank. And that's where the Bhutas void becomes more than just a scientific concept. It becomes a kind of mental experience, a way of confronting scale not through abundance but through absence, which is a bit unusual, because we tend to measure importance by what's present, by what we can see, count, and describe. The void invites us to do the opposite, to consider what it means for something to be defined by what's missing, and to realise that even in that absence there is still structure, still meaning, still part of the larger whole. If you imagine drifting through it, slowly, without any urgency, the experience might feel oddly calm. No nearby galaxies rushing past, no dense clusters pulling you in, just vast, open space, a kind of cosmic stillness. But at the same time, there's a quiet tension in that stillness, because the distances involved are so extreme that they resist intuition. You can't easily say, I'll just travel a little farther and see what's there. Farther doesn't behave the way it does on Earth. It stretches, it expands, it becomes something that feels almost unreachable. And yet, despite all of this, the Bhutas void is not some distant anomaly in a completely different kind of universe. It exists within the same cosmic web that includes our own galaxy. It's part of the same structure, just a very different part of it. Which means that, in a sense, we're not entirely separate from it. We're connected through the same underlying patterns, the same gravitational forces, the same history of cosmic evolution. It's just that, where we are, matter gathered more densely, and where the void is, it didn't. That contrast is what makes it so compelling, because it shows that the universe can take the same basic ingredients and produce very different outcomes. Regions filled with galaxies, light, and activity, and regions where those things are almost entirely absent. There's a quiet expectation built into the way we think about the universe. Not something we usually say out loud, but something that sits in the background of how we imagine it working. If you take a large enough region of space, you expect to find galaxies there. Maybe not evenly spaced, maybe not perfectly arranged, but present. Enough of them that, if you were to travel through that region, You wouldn't feel completely alone for very long. That expectation comes from everything we've observed. Look in almost any direction, and you'll find galaxies. Look deeper, and you'll find more. Larger surveys reveal patterns, yes, but also consistency. Even the quieter regions of space still contain something. So when astronomers mapped the Bhuta's void, they weren't expecting perfection, but they were expecting more than what they found. Because based on the average density of galaxies in the universe, a region that large should contain hundreds, perhaps thousands of galaxies, not packed tightly together, but scattered throughout. Enough to form at least a faint structure, enough that if you plotted them on a map, you'd still see a pattern emerging. But inside the Bhuta's void, that expectation doesn't hold. Instead of a faint structure, you find something much closer to silence, a handful of galaxies, just a few. And that's where things become quietly puzzling, because this isn't just a case of fewer than average, it's a case of far fewer than expected, the kind of difference that makes you pause and ask whether something unusual happened. To understand why this matters, it helps to think about how galaxies form in the first place. In the early universe, matter wasn't perfectly smooth. There were tiny fluctuations in density. Some regions had slightly more matter than others. Over time, gravity amplified those differences. Regions with more matter pulled in even more, growing denser. Regions with less matter lost what little they had to their surroundings. This process, repeated over billions of years, created the large-scale structure we see today. Galaxies formed where matter gathered, clusters formed where galaxies gathered, and in between, voids formed where matter was pulled away. But here's the important part. Even in regions that started with slightly less matter, you'd still expect some galaxies to form. The differences at the beginning were small, not absolute. So while voids would be less dense, they wouldn't be completely empty. They would still contain a scattering of galaxies. That's what makes the Bhuta's void so interesting, because it seems to have taken that process to an extreme. It's not just underdense, it's exceptionally underdense. As if, in this particular region, the usual rules of structure formation were followed, but pushed much further than anywhere else. Now, one way to think about this is through probability. Imagine you're distributing a large number of points across a space. If the distribution is mostly uniform, you might get small clusters and small gaps. Occasionally you might get a larger gap just by chance. But a gap as large as the Bhuta's void, with so few points inside it, is statistically unusual, not impossible, but rare enough that it stands out, and that's exactly what astronomers noticed. When they compared the Bhuta's void to other voids, it wasn't just another example, it was one of the most extreme cases known, which raises a natural question. Why this region? Why here in this part of the universe did galaxies fail to appear in the numbers we'd expect? One possibility is that it's simply a rare fluctuation. In a universe as large as ours, even unlikely configurations can occur. Given enough space, enough time, enough variation, you're bound to find regions that deviate strongly from the average. In that sense, the Bhuta's void might just be an extreme example of a normal process, a statistical outlier, but there's another way to look at it. Instead of thinking about what's missing, we can think about what happened to the matter that might have been there. Because the universe is dynamic, matter doesn't stay in one place, it moves, it flows under the influence of gravity. In regions that become voids, matter tends to drift outward, toward denser areas. It's almost as if the void is slowly being emptied, with matter pulled away into surrounding structures. Over time, this process makes the void even emptier, a kind of self-reinforcing effect. Less matter leads to less gravitational pull, which leads to even less matter staying behind. So perhaps the Bhuta's void didn't start out dramatically empty. Perhaps it started as a slightly underdense region, like many others, but over billions of years, matter gradually flowed out of it, leaving behind a region that became more and more sparse, until eventually it reached the state we observe today, place where galaxies are not entirely absent, but so rare that they feel almost misplaced. That idea leads to an interesting image. Instead of thinking of the void as something static, you can imagine it as something that has been slowly cleared out over time, not by any active force, but by the gentle, persistent pull of gravity elsewhere. The surrounding filaments and clusters act like attractors, drawing matter away, and the void in response expands and empties. Now let's return to those galaxies that are inside the void, because their existence is just as interesting as the absence of others. These galaxies are often isolated, far from their nearest neighbours, living in an environment very different from the dense regions where most galaxies reside, and that environment likely affects how they evolve. In dense regions, galaxies interact frequently. They merge, collide, exchange material. These interactions can trigger bursts of star formation, reshape galaxies, and influence their structure. Inside the Bhuta's void, those interactions are rare. A galaxy might go billions of years without encountering another, which means it evolves in relative isolation, a kind of cosmic solitude. That solitude might sound peaceful, and in a way it is, but it also means fewer opportunities for change driven by interaction. The galaxy's evolution becomes more dependent on its internal processes, its own stars, its own gas, its own dynamics, and that makes these galaxies valuable to study, because they offer a glimpse of what galaxy evolution looks like in the absence of strong external influences. But even with those few galaxies present, the overall picture remains the same. There are far fewer galaxies than there should be, and that discrepancy is what keeps drawing attention. It's a reminder that our expectations, even when based on well-tested theories, are not always perfectly met. The universe has a way of producing outcomes that are just a little more extreme than we anticipate. Not enough to break the rules, but enough to stretch them, and in doing so, it invites us to look more closely, to refine our understanding, to ask better questions. In this case, the question isn't just why is this region empty? It's what does this emptiness tell us about how the universe formed and evolved? Because the absence of galaxies isn't just a curiosity, it's a clue, a piece of the larger puzzle, a sign that, in this region, the balance between matter and gravity played out in a slightly different way, and by studying that difference, we learn more about the whole. If we take a gentle step back from the emptiness for a moment, something interesting begins to come into view, because the Bhuta's void doesn't exist on its own. It isn't floating somewhere separate, disconnected from everything else. It's part of a much larger pattern, a pattern that, once you start to see it, changes the way the entire universe looks. This pattern is often called the cosmic web, and despite the name, it's not something you'd notice by simply looking up at the night sky. From Earth, the universe feels scattered. Stars here, galaxies there, vast darkness in between. But when astronomers map the positions of millions of galaxies across enormous distances, a different picture emerges, one that feels surprisingly organized. Instead of randomness, there are threads, long, thin filaments of galaxies stretching across space, sometimes hundreds of millions of light years in length. These filaments connect to one another, forming a network. At the points where multiple filaments intersect, galaxies gather into clusters, dense regions where gravity has pulled matter together over billions of years. And between those filaments and clusters, there are gaps, large open regions where matter is scarce, voids. So rather than thinking of the universe as a uniform spread of galaxies, it's more accurate to think of it as something structured, a kind of three-dimensional network with matter tracing out its shape. If you were to visualize it, it might remind you of something familiar. Perhaps the pattern of foam on the surface of water, where bubbles cluster together, leaving empty spaces between them. Or the structure of a sponge, with solid regions surrounding pockets of air. Or even the branching of roots underground, spreading outward, connecting in complex ways. None of these are perfect comparisons, but each of them captures a piece of the idea. The universe, on its larger scales, has a kind of architecture, and the Botez void is one of the spaces within that architecture. Now, how did this structure form? To answer that, we need to go back just a little to the early universe. Right after the Big Bang, the universe was hot, dense, and remarkably smooth. Not perfectly smooth, but close. There were tiny fluctuations in density, regions where matter was slightly more concentrated than others. These differences were incredibly small. So small that, at the time, they might have seemed insignificant, but gravity has a way of amplifying even the smallest differences. Over time, regions with slightly more matter began to pull in more material. They grew denser. Regions with slightly less matter lost material to their surroundings. They became emptier. This process continued over billions of years, slowly, steadily, shaping the universe into the structure we see today. Dense regions became filaments and clusters. Underdense regions became voids, and the boundaries between them became the cosmic web. One of the interesting things about this process is that it doesn't happen evenly. Gravity doesn't pull matter inward from all directions at the same rate. Instead, matter tends to collapse along certain directions first, forming sheets. Then those sheets collapse into filaments, and eventually matter flows into the densest points, forming clusters. So the cosmic web isn't just a random network, it's the result of a very specific sequence of gravitational events, a kind of slow-motion shaping of the universe. Now, here's where things become particularly relevant to the Botez void. As matter flows into filaments and clusters, it leaves behind regions that become increasingly empty. Those regions expand, not because something is pushing them outward directly, but because the surrounding matter is pulling away. It's a subtle difference, but an important one. The void grows because everything around it is gathering elsewhere, and over time that process can create very large voids. The Botez void is one of the most extreme examples of this. A region where matter didn't just fail to gather, it was gradually drawn away, leaving behind an area of space that became more and more underdense. And that's why it's helpful to think of the void not as an isolated feature, but as part of the web. Its boundaries are defined by the surrounding filaments and clusters. Its shape is influenced by the distribution of matter around it. Its existence is tied to the same processes that created galaxies and clusters elsewhere. In other words, the void and the web are two sides of the same story, one defined by presence, the other by absence, but both shaped by the same underlying physics. Now let's imagine what this structure might look like if you could see it from far enough away. Not with your eyes, but with some kind of cosmic perspective. You wouldn't see individual stars, you wouldn't even see individual galaxies. Instead, you'd see a faint glowing network, threads of light stretching across darkness, clusters appearing as brighter knots where those threads intersect, and between them, vast regions where the glow fades almost entirely. The Botez void would appear as one of those darker regions, a large, roughly spherical area where the network thins out dramatically, surrounded by brighter, denser structures, almost like a bubble in the fabric of the universe. And that image, while simplified, captures something important, because it shows that the universe isn't just made of objects, it's made of relationships, connections, flows of matter and energy that shape where things end up. Galaxies don't just exist in isolation, they're part of a larger system, influenced by their surroundings, pulled along by the gravitational landscape of the cosmic web, and voids like the Botez void are part of that landscape. They influence how matter moves. They affect the paths galaxies take. They shape the evolution of the universe on the larger scales. In fact, galaxies near the edges of voids often experience what's called outflow. They move away from the void toward denser regions, not because the void is pushing them, but because the surrounding structures are pulling them. It's a bit like standing in a wide valley surrounded by hills. You don't feel a force pushing you out of the valley, but gravity pulls you toward the higher ground around it. Over time, that movement empties the valley even further. And in the universe, that process happens on scales far beyond anything we experience. The Botez void, then, is not just a quiet region. It's part of a dynamic system, a place where matter has flowed away, leaving behind a kind of cosmic stillness. But that stillness is the result of motion, of billions of years of gradual change. Which brings us back to something we touched on earlier, the idea that emptiness in the universe is not just the absence of something, it's the result of something happening, a process, a history. The Botha's void didn't simply appear as an empty space, it became empty over time, shaped by the same forces that built everything else. And that's what makes it so interesting, because by studying the void, we're not just looking at what's missing, we're looking at the outcome of a process that operated across the entire universe, a process that created both the densest clusters of galaxies and the emptiest regions between them. When you begin to see the universe as a kind of vast structure with filaments and clusters woven together across unimaginable distances, something else naturally comes into focus, the spaces in between. Not as an afterthought, not as empty leftovers, but as part of the design itself. Because those spaces, those quiet regions between the threads of the cosmic web, are everywhere. They are not rare. They are not exceptions. They are in many ways the dominant feature of the universe, and these regions have a name: voids. Now, the Botha's void is one of the most famous examples, but it's far from the only one. In fact, the universe is filled with voids of all sizes. Small ones, relatively speaking, spanning tens of millions of light years, larger ones stretching across hundreds of millions, and then occasionally extreme cases like the Botha's void, where the scale and emptiness become particularly striking. So rather than thinking of voids as unusual, it's more accurate to think of them as a natural outcome of how the universe organises itself. They are the quiet gaps between the busy regions, the low-density zones where matter has thinned out over time. But what exactly defines a void? That's a slightly more nuanced question than it might first appear, because space doesn't come with clear boundaries. There are no sharp edges separating a void from a filament or a cluster. Instead, everything transitions gradually. Densities increase or decrease smoothly, rather than abruptly. So astronomers define voids using thresholds. They look at the average density of galaxies in a given region, and if that density drops below a certain level, the region can be classified as a void. It's not a perfect definition, but it's a practical one. And using that approach, scientists have identified countless voids across the observable universe. Some are relatively shallow, meaning they're only slightly less dense than average. Others are much deeper, with significantly fewer galaxies. And then there are the extreme voids, where the density drops so low that galaxies become rare. The Botha's void belongs to that last category, but to really understand what makes it special, it helps to first understand what a typical void looks like. Imagine a region of space that's, say, 50 million light-years across. Inside it, you might still find dozens of galaxies. They're just more spread out than usual. Instead of being part of dense clusters or filaments, they drift in relative isolation. If you were travelling through such a void, you wouldn't feel completely alone. You'd still encounter galaxies from time to time. The distances between them would be larger, but not overwhelming. There would still be a sense of presence. Now compare that to something like the Botha's void. The scale increases, the number of galaxies decreases dramatically, and the distances between them become enormous. That's the difference between a quiet region and a truly empty one. Now here's something that might seem a little counterintuitive. Voids are not static. They change over time. In fact, they tend to grow. This happens because of the way gravity shapes the universe. In dense regions, gravity pulls matter inward. Galaxies cluster together, forming larger and larger structures. In underdense regions, the opposite effect occurs. Matter is pulled away toward the surrounding filaments and clusters. As a result, the void becomes emptier, and as it becomes emptier, it also expands, not because something is pushing it outward directly, but because the surrounding matter is moving away. It's a bit like watching a crowd of people gradually gather in certain areas, leaving other areas more and more open. The open spaces don't actively expand, but they grow as people leave them. Over billions of years, this process can create very large voids, and it also means that voids are not just passive features. They play an active role in the evolution of the universe. They influence how matter flows. They affect the motion of galaxies. They shape the large-scale structure we observe today. There's another interesting aspect of voids that's easy to overlook. Despite being mostly empty, they are not completely devoid of activity. Inside a void, there are still galaxies, gas, and dark matter, just in much lower quantities. And because of that low density, the environment inside a void is quite different from the environment in dense regions. Galaxies inside voids tend to be more isolated. They experience fewer interactions with other galaxies, fewer collisions, fewer mergers, fewer external influences. This can affect how they evolve. For example, galaxies in dense regions often undergo dramatic changes due to interactions. They can merge, triggering bursts of star formation. They can be stripped of gas, altering their structure. Inside a void, those processes are much less common. A galaxy might evolve more slowly, more quietly. Its changes driven mostly by internal processes rather than external events. In a way, void galaxies live a different kind of cosmic life, less crowded, less eventful, but still part of the same universe. Now let's think about how voids are arranged. They're not scattered randomly. They fit together with filaments and clusters to form the cosmic web. Each void is surrounded by denser structures, and those structures, in turn, surround other voids. It's a continuous pattern, a kind of interlocking system of matter and emptiness. If you could trace out all the voids in the universe, you'd see that they fill a significant portion of its volume. In fact, most of the universe's space is made up of voids, not because there are more of them in number, but because they occupy so much room. The dense regions where galaxies cluster actually take up a relatively small fraction of the total volume, which leads to an interesting shift in perspective. When we think about the universe, we often focus on the things that are there. Stars, galaxies, clusters. But in terms of sheer volume, the universe is mostly empty. Voids dominate. The structures we see are like threads and nodes within that vast emptiness. And the Boater's void is one of the clearest examples of that idea. A region where the absence of matter becomes the defining feature. Now there's also a subtle hierarchy among voids. Some are small and shallow, others are larger and deeper, and sometimes smaller voids can merge over time, forming larger ones. This merging process is similar, in a way, to how galaxies can merge. But instead of matter coming together, it's emptiness expanding. Smaller underdense regions combine, creating a larger underdense region. And over time, that larger void becomes more pronounced. This might be part of how something like the Boater's void formed. Not as a single, isolated event, but as the result of multiple smaller voids growing and merging over billions of years. If that's the case, then the void we see today is the outcome of a long, gradual process. A kind of cosmic evolution that favours both clustering and emptiness. Now here's a gentle way to think about the role of voids. Imagine the universe as a kind of breathing system. Dense regions are where matter gathers, compresses, becomes active. Voids are where matter has moved away, leaving behind open space. Together, they create a balance, a rhythm. Not in the sense of something pulsing back and forth quickly, but in the sense of a long, slow process unfolding over billions of years. Matter flows inward in some places, outward in others. Structures grow, voids expand, and the overall pattern becomes more pronounced. The Boater's void, then, is not just an empty space. It's part of that rhythm, an extreme example of the outward side of the process, a region where the quiet has become particularly deep. By now, the idea of voids might feel a little more familiar. Large, quiet regions between the filaments of the cosmic web, places where galaxies are fewer, where matter has thinned out over billions of years, where gravity has quietly pulled things elsewhere. And if that's the case, then a natural thought begins to form. If voids are common, then what makes the Bhuta's void so special? Why does this particular region stand out when the universe is already full of gaps? The answer, gently put, is not just that it's a void, it's how extreme it is. Because while most voids follow a kind of familiar pattern, the Bhuta's void seems to stretch that pattern to its limits. Let's take this step by step. In a typical cosmic void, you would still expect to find a noticeable number of galaxies. They would be spread out, yes, but present. If you map that region, you'd still see a faint pattern of points, a kind of diluted version of the cosmic web. The emptiness would feel relative, not absolute. You'd still have reference points, still have something to anchor your sense of space. But in the Bhuta's void, those anchors become rare. So rare that the void doesn't just feel quiet, it feels interrupted, as if the usual pattern of galaxy formation simply didn't happen in the same way. Now, this isn't a case of there being no galaxies at all. There are a few. But compared to what we'd expect for a region of that size, the number is strikingly low. It's the difference between walking through a sparsely populated town and walking through a place where you begin to wonder if anyone ever built anything there at all. And that difference is what draws attention, because it suggests that something about this region is not just typical emptiness, but something closer to an extreme outcome. Now, let's consider size again, but in a slightly different way. We've already talked about how large the Bhuta's void is, about 330 million light-years across. That alone places it among the largest known voids. But size by itself isn't the only factor. It's the combination of size and underdensity. There are other large voids. There are other empty regions. But not all of them are both this large and this empty at the same time. It's that combination that makes the Bhuta's void stand out. A vast region with far fewer galaxies than expected. Now, there's another subtle aspect that makes it different. Shape. Many voids are somewhat irregular. They stretch and twist, shaped by the surrounding filaments and clusters. They don't always have a clear, simple form. The Bhuta's void, while not perfectly uniform, is often described as roughly spherical, a kind of large, rounded region of underdensity. That might not sound particularly important at first, but it hints at something interesting. It suggests that the processes shaping this void may have been relatively consistent in all directions, that the clearing out of matter happened in a way that produced a fairly coherent structure, rather than a jagged or uneven one. Now, let's return to the idea of expectation, because much of what makes the Bhuta's void unusual comes from how it compares to what we think should be there. Based on our models of the universe, we can estimate how galaxies should be distributed. Not perfectly, but statistically. We know how matter clumps together over time. We know how density fluctuations grow. We know how voids form and expand. And when we apply those models to a region the size of the Bhuta's void, we expect to find more galaxies than we actually observe. Not dramatically more in every case, but enough to make the difference noticeable. So the void doesn't just look empty, it looks emptier than predicted. And that's where things become particularly interesting, because when observations don't quite match expectations, it invites closer examination. It doesn't necessarily mean something is wrong, but it does mean there's something to understand. One possibility, as we touched on earlier, is that the Bhuta's void is simply a statistical outlier. In a universe this large, rare configurations can and do occur. Given enough volume, you're bound to find regions that deviate significantly from the average. In that sense, the void might be an extreme but natural result of the same processes that create all voids, just taken a bit further, but there's another perspective. Instead of focusing on how unlikely it is, we can look at what might have caused it to become so extreme. Perhaps the initial conditions in this region were slightly different. Maybe the density fluctuations here were lower than average from the very beginning. Even a small difference amplified over billions of years could lead to a much larger void. Or perhaps the surrounding regions were particularly effective at pulling matter away. Strong filaments, dense clusters, acting like gravitational attractors, drawing material outward and leaving the void behind. In that scenario, the void becomes not just a passive gap, but the result of active processes happening around it, a region shaped by what's happening at its edges. There's also the possibility that multiple smaller voids merged over time. Instead of one region becoming empty, several underdense regions gradually expanded and combined, creating a larger, more pronounced void. This idea fits with what we know about how voids evolve. They don't remain fixed, they grow, shift, and sometimes merge. So the Bhuta's void we see today might be the result of a long history of smaller voids coming together. Now here's something that adds another layer to the story. Even though the Bhuta's void is extreme, it doesn't break the laws of physics. It doesn't require new forces or unknown phenomena to exist. Everything about it can still be explained within our current understanding of cosmology. It's just at the edge of what that understanding predicts, and that's often where the most interesting discoveries happen. Not in places where everything behaves exactly as expected, but in places where the behaviour stretches those expectations just enough to make us look twice. Now let's think about what this means on a more intuitive level. If you were to travel through a typical void, you might notice the emptiness, but you'd still feel connected to the surrounding universe. Galaxies would appear occasionally. There would be a sense of continuity. In the Bhuta's void, that continuity becomes much harder to perceive. The distances between galaxies become so large that each one feels isolated. The structure becomes so faint that it almost disappears. It's not just a quieter version of the universe, it's a region where the usual patterns are barely visible. And that difference, subtle as it might seem in words, becomes profound when you try to imagine it. Because it shifts the experience from less of something to almost none of something, from variation to near absence. And that's what makes the Bhuta's void feel so different from other voids. It's not just part of the pattern, it's an extreme expression of it. A place where the quiet has become deeper than usual, where the gaps have widened beyond expectation, where the absence of galaxies becomes the defining feature. Let's slow things down a little more now, because up to this point we've been talking about structure, scale, expectations and patterns. We've been looking at the Bhuta's void from the outside as something to measure, to map, to understand. But there's another way to approach it. Not as observers looking in, but as travellers drifting through it. So imagine, just for a moment, that you are there. No rush, no urgency, no mission to complete. Just gently moving through space, carried along at a steady pace with nothing pressing you forward. At first, the journey might feel familiar. You pass a galaxy, perhaps a distant spiral, its faint glow stretching across the darkness. Then another, much farther away. The kind of distances that already feel large, but still understandable within the context of space. There's a rhythm to it. Presence, then distance. Light, then darkness. Enough variation that your mind can keep track of where you are. But slowly, almost without noticing, that rhythm begins to change. The gaps between galaxies grow wider. The light becomes more sparse. You travel longer and longer without seeing anything nearby. At first, it might not feel like much of a difference, just a quieter region. But as time passes, something shifts. You begin to realize that the usual markers of space, the things that help you orient yourself, are fading. There are fewer reference points, fewer nearby galaxies, fewer signs that you're moving through a structured environment, and eventually you reach a point where you look around and see almost nothing at all. Not absolute darkness, because there are still distant galaxies far beyond your immediate surroundings, but they're so far away that they feel more like a background than a presence. You've entered the Bhuta's void. Now, here's where the experience becomes a little unusual, because on Earth, or even within a galaxy, we're used to having a sense of scale. We know how far things are, roughly. We have landmarks, distances we can compare, ways to measure progress. Inside the void, those anchors begin to disappear. There's no nearby structure to give you context. no cluster of galaxies to pass through, no filament to follow, just vast open space, and that changes the way distance feels. Because distance isn't just about how far something is, it's also about how often you encounter something along the way. If you walk through a city, even a large one, you're constantly passing buildings, streets, people. The distance is broken into smaller, manageable pieces. If you walk through an open desert, the same distance feels longer. There are fewer interruptions, fewer reference points. Inside the Buddha's void, that effect is taken to an extreme. The journey isn't just long, it's uninterrupted. You could travel for what feels like an eternity without encountering anything nearby. And that creates a very particular kind of experience, a kind of stillness that isn't just quiet but expansive. Now imagine trying to navigate in such a place. On Earth we use landmarks, mountains, buildings, coastlines. In space we might use stars, galaxies, clusters. But inside the void those markers are distant. Too distant to provide immediate guidance. You might still know your direction based on distant references, but the sense of moving through something becomes less clear. It's more like drifting within something that doesn't change very much as you move. And that can feel disorienting in a subtle way. Not because you're lost, but because the environment itself doesn't provide the usual cues. Now, there's another aspect to this that's worth considering. Time. Not in the physical sense we discussed earlier, but in the way it feels. When you're surrounded by activity, by events, by changes, time tends to feel structured. One thing leads to another. Moments are marked by transitions. But in an environment where very little changes, that structure softens. Inside the Buddha's void, there are fewer events, fewer interactions, fewer changes in your surroundings. And that can make time feel stretched. Not because time itself is different, but because there are fewer markers to divide it. It's a bit like waiting in a very quiet room. With nothing happening, each moment feels longer. But here, that effect isn't lasting minutes or hours. It extends across vast stretches of space. Now, let's consider what you would actually see, not with perfect clarity, but as an impression. The nearest galaxies would be incredibly far away, much farther than what we're used to when we think about intergalactic space. They would appear faint, small, almost like distant points of light that don't change much as you move. The sky, if you can call it that, would feel darker. Not completely empty, but lacking the richness we associate with regions filled with galaxies. There would be no dense clusters lighting up the distance. No nearby structures to break up the emptiness, just a few scattered points separated by enormous distances, and in between, darkness. Not the kind of darkness that feels heavy or enclosed, but a kind of open, boundless darkness. Now, here's something interesting. Despite all this emptiness, you wouldn't be in danger in the usual sense. There's no force pushing you, no hazard unique to the void itself. It's not hostile, just quiet. The physics inside the void are the same as anywhere else. Gravity still works, light still travels, time still passes. It's not a different kind of space, it's just a different kind of environment, which makes the experience all the more intriguing. Because it shows that you don't need anything unusual or exotic for something to feel completely unfamiliar. Sometimes, it's enough to take something we understand, space, and remove most of what we expect to find in it, and suddenly the experience changes. Now let's bring in one more perspective. Imagine not just drifting through the void, but living inside it, not as a traveller passing through, but as part of one of those few galaxies within it. Your galaxy would still have stars, still have planets, still have structure. From within it, life might feel normal, but when you look outward, the universe would appear very different. The nearest galaxies would be much farther away. The large-scale structure of the universe would be harder to perceive. You might not easily detect the cosmic web. Instead, you might conclude that the universe is more sparse than it actually is. That the distribution of galaxies is more uniform but much less dense. In other words, your understanding of the universe would be shaped by your environment, and inside the Buddha's void, that environment is defined by absence, which is a subtle but powerful idea, because it reminds us that our perspective is always local. We interpret the universe based on where we are within it. And if we happen to be inside a region like this, our picture of the cosmos might look very different. Now, as you continue to drift through this imagined journey, something else becomes clear. The void is not completely featureless. It has a boundary, not a sharp edge, but a gradual transition. As you move toward the edges, galaxies begin to appear more frequently. The distances between them shrink. The structure becomes more apparent. Eventually, you leave the void behind and re-enter the denser regions of the cosmic web. And with that, the familiar patterns return. Clusters, filaments, interactions. The universe feels full again. That contrast is important, because it highlights just how different the void is from its surroundings. It's not just a slightly quieter region. It's a place where the usual patterns fade almost entirely, and then, just as gradually, return. Far from the crowded intersections of the cosmic web, where galaxies gather and interact like busy crossroads, there exist places where that sense of community fades almost entirely. And within the Buurt's void, this fading reaches one of its most extreme forms, because despite everything we've said about emptiness, the void is not completely devoid of galaxies. There are a few, scattered, distant, and separated by enormous stretches of space, and those galaxies, quietly drifting within that vast underdense region, are often described as some of the loneliest in the universe, not because they are aware of their isolation, of course, but because of how profoundly separated they are from everything else. To understand what makes them so unusual, it helps to first think about what a typical galaxy experiences. In most parts of the universe, galaxies are not alone. They exist in groups, clusters, and along filaments. They have neighbours, sometimes close enough that their gravitational pull begins to interact. Over time, those interactions can lead to mergers, two galaxies slowly spiralling toward each other, their stars weaving together, their structures reshaped by the encounter. Even when galaxies don't merge, they can still influence one another. They can exchange gas, trigger bursts of star formation, alter each other's motion. In dense regions, this kind of interaction is common. It's part of the normal life of a galaxy. But inside the Buddha's void, that environment changes dramatically. The distances between galaxies are so large that interactions become rare. Not just uncommon, rare enough that a galaxy might go billions of years without a significant encounter. Imagine that for a moment. A galaxy evolving almost entirely on its own. No nearby neighbours to disturb it. No collisions to reshape it. No dense environment to influence its development. Just its own stars, its own gas, its own internal processes. It's a kind of cosmic isolation that's difficult to find elsewhere. And that isolation has consequences. Because when galaxies are left alone, their evolution follows a different path. In crowded regions, interactions can trigger rapid changes. A merger might compress gas, leading to intense periods of star formation. A close pass with another galaxy might distort its shape, pulling out long tidal tails of stars. These events add complexity, variety, and sometimes chaos to a galaxy's history. Inside the void, those events are largely absent, so the galaxies there tend to evolve more quietly, more gradually. Their star formation might proceed at a slower, steadier pace. Their structures might remain more stable over time. They become, in a sense, more pristine, less altered by external forces. Now, that doesn't mean they're simple. Galaxies are complex systems, even in isolation. Stars are born and die. Gas clouds collapse and disperse. Supernovae inject energy into their surroundings. Black holes influence the motion of nearby matter. All of that still happens, but it happens without the added layer of frequent external interaction, which makes these galaxies particularly interesting to astronomers, because they offer a glimpse of what galaxy evolution looks like when it's driven mostly from within, a kind of natural laboratory for studying internal processes. Now, let's return to the idea of loneliness. Because while it's a useful way to describe these galaxies, it also highlights something deeper about scale. In our everyday experience, being alone usually means being separated by distances we can still comprehend. A few meters, a few kilometers, even a few thousand kilometers still feels within reach. But in the Bhuta's void, the separation between galaxies is measured in millions of light years, not just distance, but time. Light itself takes millions of years to travel from one galaxy to another, which means that even communication, if it were possible, would be delayed on timescales far beyond anything we experience. A signal sent from one galaxy might not reach another until long after both have changed in significant ways. In that sense, each galaxy exists in its own kind of temporal bubble, connected to the rest of the universe, but only through very slow exchanges of light and gravity. And that creates a kind of isolation that goes beyond simple distance. It's not just that galaxies are far apart, it's that the interaction between them becomes almost negligible over meaningful timescales. Now, here's something subtle but important. Even though these galaxies are isolated, they're not completely disconnected. Gravity still links everything in the universe. The large-scale structure still influences their motion. The expansion of the universe still affects how they move relative to one another. So they are still part of the cosmic web, just located in one of its quietest regions. That connection matters, because it reminds us that isolation in this context is relative. The galaxies are far apart, but not separate from the universe as a whole. They are still embedded in the same underlying structure, still influenced by the same physical laws, still evolving as part of the same cosmic story. Now imagine observing one of these galaxies from within, not as an external observer, but as someone living on a planet within it. Your night sky would look familiar in some ways. Stars within your own galaxy would still shine. Constellations would form. The Milky Way, or its equivalent, would stretch across the sky. But when you look beyond your galaxy, the view would be different. In our region of the universe, nearby galaxies are relatively accessible. Astronomers can observe them in detail. They appear as faint but distinct objects. Inside the Bhuta's void, the nearest galaxies would be much farther away. They would appear dimmer, smaller, harder to detect. The universe beyond your galaxy would seem more sparse, more distant. You might not immediately perceive the larger structure of the cosmic web. Instead, the universe might appear as a mostly empty expanse, with only a few distant points of light. And that perspective could shape how you understand the cosmos. You might conclude that galaxies are more isolated than they actually are, that the universe is less structured than it truly is. In other words, your location would influence your interpretation, which is something we touched on earlier, but becomes particularly clear here. Now, let's think about the motion of these galaxies. In denser regions, galaxies are influenced by the gravitational pull of nearby structures. They move along filaments, toward clusters, interacting with their surroundings. Inside the void, that motion is different. There's less nearby mass to influence their paths, so their motion is more subtle, more influenced by the larger scale structure than by immediate neighbours. Over time, many of these galaxies will slowly drift toward the edges of the void, not because they are being pushed out, but because the surrounding structures exert a stronger gravitational pull. This process happens gradually, over billions of years, and as it continues, the void becomes even emptier, which means that the galaxies we see inside it today might not always remain there. They may eventually move toward denser regions, becoming part of the larger structures of the universe, but for now they remain, quietly drifting, isolated but not entirely alone. And that brings us back to the idea of loneliness. Because while it's tempting to think of these galaxies as isolated in a dramatic sense, there's also something quietly peaceful about their existence. No constant interactions, no frequent collisions, just a slow, steady evolution over immense timescales, a kind of cosmic calm. Of course, that calm comes with distance so large that it challenges our usual ways of thinking. But it also offers a different perspective, a reminder that not all parts of the universe are dynamic and crowded. Some parts are quiet, expansive, unhurried, and in those places galaxies live out their lives in relative solitude. Consider for a moment the idea of sending a signal. Not a message in the usual sense, not words or images, just a simple beam of light. A pulse, perhaps, released from one side of the Bhuta's void, travelling steadily across that vast emptiness. No obstacles in its path. No dust clouds thick enough to block it. No dense clusters to scatter it significantly. Just open space. It sounds simple, and in a way, it is. Light moves at a constant speed, about 300,000 kilometers per second, no matter where it is. It doesn't slow down because space is empty. It doesn't get tired, doesn't pause, doesn't need direction. It just continues. But the simplicity of that motion is what makes the scale so striking. Because even at that speed, crossing the Bhuta's void is not a quick journey. It takes hundreds of millions of years. To say that more gently, if a photon, a single particle of light, began its journey from one edge of the void, it would travel for longer than most of the history of life on Earth before reaching the other side. That's not a delay in the sense we're used to. That's not waiting for a signal to buffer or load. That's a timescale so large that it becomes difficult to connect it to anything familiar. Now let's slow that down even further. Imagine that beam of light beginning its journey. At the moment it starts, Earth looks very different. The continents are not where they are today. The climate is different. The species that exist are different. Over the time it takes for that light to cross the void, entire evolutionary eras come and go. Species appear, thrive, and disappear. Landscapes shift, oceans change, and still, the light continues its steady motion, unaffected by all of it. By the time it reaches the other side, the universe itself has changed. Not dramatically on the larger scales, but enough that the context of that journey is no longer the same. And that's one of the subtle things about distances this large. They are not just distances in space. They are distances in time. Now, here's something that makes this even more interesting. When we observe something far away, we're not seeing it as it is now. We're seeing it as it was when the light left it. So if we were to observe a galaxy on the far side of the Bhuta's void, the light reaching us today would have begun its journey hundreds of millions of years ago. We would be looking into the past, not just a little into the past, but into a time long before our own species existed. And that's always true in astronomy. But in a region like this, where distances are so extreme, the effect becomes more pronounced. The void becomes not just a spatial separation, but a temporal one, a kind of delay built into the structure of the universe. Now, let's think about what that means for interaction. If two galaxies are separated by a few million light years, they can still influence each other over time. Gravity travels at the speed of light, so changes in one galaxy eventually affect the other. Signals, in principle, could be exchanged, though the timescales are long. But inside the Bhuta's void, the distances between galaxies can be tens or even hundreds of millions of light years, which means that any influence, gravitational or otherwise, takes an enormous amount of time to propagate. If something were to change in one galaxy, the effect on another might not be felt until long after both have evolved significantly. In that sense, each galaxy becomes somewhat isolated, not just in space, but in time. Connected, yes, but only through very slow processes. Now, there's a gentle way to think about this. Imagine you're in a large, quiet room. You speak and your voice echoes, but instead of hearing the echo a fraction of a second later, you hear it hours later, or days later. The connection is still there, but it's stretched. The feedback is delayed to the point where it no longer feels immediate. Inside the Bhuta's void, that kind of delay exists on a cosmic scale. Now let's shift perspective slightly. Instead of sending light across the void, imagine receiving it. A photon arrives at your location after travelling for hundreds of millions of years. It carries information about where it came from, the state of a distant galaxy, the light from its stars, the structure it had at the moment the photon began its journey. But that information is old. By the time it reaches you, the galaxy that emitted it has already changed. Stars have moved, new stars have formed, others have died, perhaps even entire structures have shifted. So what you're seeing is not the present, it's a kind of historical snapshot, and that's always true in astronomy, but in the context of the void it becomes particularly striking. Because the distances are so large that the snapshots are separated by vast spans of time. Now, here's something subtle. Despite all this, the speed of light itself doesn't change. It remains constant regardless of the emptiness. In fact, the lack of matter means that light can travel through the void with very little interference. There's less gas, less dust, fewer obstacles. So in some sense, the void is an ideal environment for light to move freely, unimpeded, undisturbed. Which creates an interesting contrast. The region is empty, but that emptiness allows light to travel cleanly. The journey is long, but the path is clear. Now, let's return to the idea of crossing the void. If you were to imagine a journey at the speed of light, which we can't physically achieve but can still think about, the experience would be unusual. From the perspective of the light itself, no time passes. But from the perspective of everything else, hundreds of millions of years unfold. That contrast between perspectives is one of the more intriguing aspects of physics. But even without going into that level of detail, the key idea remains. Crossing the void is not just about distance, it's about duration, about the passage of time on scales that are difficult to relate to. Now, let's bring this back to something more intuitive. In everyday life, we often think of communication as something immediate. You send a message and it arrives almost instantly. Even when there's a delay, it's measured in seconds, maybe minutes, rarely more. In the universe, especially in regions like the Bootes void, communication is fundamentally different. It's slow, not because of any limitation in technology, but because of the sheer scale of space. Even the fastest possible signal, light, takes an enormous amount of time to travel. And that changes the nature of connection. It means that events are not synchronized across large distances. Different parts of the universe are effectively living at different times, depending on how far apart they are. Now here's one more way to think about it. Imagine drawing a line across the void, from one edge to the other. That line represents a path through space, but it also represents a path through time. Every point along that line corresponds to a different moment in the history of the universe, depending on how you observe it. The farther away you look, the further back in time you're seeing. So the void becomes not just a region of space, but a kind of stretched out timeline, a place where distance and time are deeply intertwined. And that idea, while subtle, helps explain why the Bootes void feels so different from anything we experience. It's not just large, it's temporally vast, a region where even light, moving at its constant, unchanging speed, takes an extraordinary amount of time to cross. Step outside the familiar rhythm of nearby space, and something subtle begins to shift. Not in the equations, not in the laws of physics, but in the way time feels when you try to place yourself within a region like the Bootes void. Because here, distance and time are so tightly intertwined that separating them becomes difficult. We've already touched on how long it takes light to cross this vast region, hundreds of millions of years, a duration so long that it quietly dissolves into abstraction if you try to hold onto it too firmly. But instead of focusing on the number itself, let's consider what that duration does to your sense of sequence. On Earth, time is marked by change, day becomes night, seasons shift, events follow one another in a steady, recognizable pattern. Even in space, within galaxies or clusters, there is still motion, interaction, activity. Stars form and die, galaxies drift, collide, evolve. There is a sense of progression. But inside the Bootes void, that sense becomes more diffuse. Not because time is behaving differently in a physical sense, but because the markers of time become fewer. fewer interactions, fewer events, fewer changes in your immediate surroundings, and without those markers, time begins to feel less structured. It stretches, not in reality, but in perception. Let's approach this gently. Imagine sitting in a quiet room. No clock visible, no sounds, no interruptions, no tasks to complete. At first, time feels normal. A minute passes, then another. But as the stillness continues, something changes. Without events to divide your attention, each moment becomes less distinct. Time doesn't stop, but it becomes harder to measure internally. It feels longer, softer, less defined. Now extend that idea outward, not to minutes or hours, but to vast cosmic distances. Inside the void, the events that would normally give structure to time are spread far apart. Galaxies are distant. Interactions are rare. Changes are slow. And so, if you imagine yourself drifting there, time begins to take on a different character. Not slower exactly, but less punctuated, more continuous. Now, there's another layer to this. In regions of space where galaxies are close together, events can influence one another more directly. A burst of star formation in one galaxy might be triggered by an interaction with another. Gravitational forces shape motion on relatively short cosmic timescales. There's a sense of cause and effect that, while still vast, feels somewhat connected. Inside the Buddha's void, that chain of influence becomes stretched. If something happens in one galaxy, its effects take an extraordinarily long time to reach another. Light carries information, but it travels slowly compared to the scale of the void. Gravity propagates at the same speed. So interactions are not just rare, they are delayed, separated by immense spans of time, which means that each galaxy, in a sense, evolves in its own timeline, still part of the universe but less synchronized with its surroundings. Now, this doesn't change the fundamental nature of time. Seconds still pass, physics still operates as it always does. But the experience of time, if you imagine it from within that environment, becomes different. It becomes quieter, more stretched out, less tied to immediate change. There's also something interesting about anticipation in such a place. On Earth, we're used to waiting for something to happen, for a message to arrive, for an event to unfold. And even when the wait feels long, it's usually bounded by familiar scales: minutes, hours, days. Inside the void, the idea of waiting becomes almost abstract, because the timescales involved are so large that anticipation loses its usual meaning. If a signal takes hundreds of millions of years to arrive, it's no longer something you can wait for in any practical sense. It becomes part of a much larger flow of time, something that unfolds independently of any single observer. Now let's bring this back to something more personal. Because even though we can't physically experience the Buddha's void, thinking about it can gently shift how we perceive time in our own lives. We're used to thinking of time as something that moves quickly or slowly depending on what we're doing. Busy moments feel short, quiet moments feel long. But those variations are small compared to the scales we're discussing here. In the void, the absence of frequent change creates a kind of baseline stillness, a backdrop where time doesn't feel rushed, not because it's slower, but because there's less to divide it, and that idea can be surprisingly calming, a reminder that time doesn't always need to be filled with events to be meaningful, that there can be value in stretches of quiet, in moments where nothing much seems to happen. Of course, the Buddha's void takes that idea to an extreme, a scale so large that it moves beyond everyday experience. But the principle is still there. Now there's another subtle aspect worth considering. When we look across the void, we're looking across time. Every distant galaxy we see is a snapshot from the past. And because the distances are so great, those snapshots are separated by vast intervals, which means that, in a sense, the void contains a kind of layered history, different regions reflecting different moments in the universe's timeline. Not because time is different in each place, but because light takes so long to travel. So if you could somehow observe multiple galaxies across the void simultaneously, you would be seeing them at different stages of their evolution. A kind of patchwork of cosmic history, spread across space. And that adds another dimension to the idea of time feeling different. It's not just about how time passes locally, it's about how time is revealed across distance. Now let's return to the imagined journey. You're drifting through this vast, quiet region. There's no immediate sense of urgency, no nearby events demanding attention, just steady motion through space. In that environment, your sense of time might begin to align more with the scale of the void itself. Not measured in minutes or hours, but in longer, softer intervals. Changes become gradual, transitions become subtle, moments blend into one another, and that blending creates a kind of calm. Not the calm of silence alone, but the calm of reduced complexity. Fewer interactions, fewer disruptions, more continuity. Of course, this is all an imagined perspective. In reality, any observer would still carry their own internal sense of time, their own rhythms, their own measurements, but the environment they're in would shape how that time feels, just as a quiet room feels different from a busy street. Now extend that idea to a region hundreds of millions of light years across, and the effect becomes more pronounced. Sometimes, when we hear that a place is empty, a quiet question follows not far behind. Empty, or just difficult to see? Because the Bhuta's void, for all its vastness and apparent absence of galaxies, is still part of the same universe that hides so much from direct observation. And that raises a gentle possibility. What if some things are there, but simply not visible in the ways we usually look? To explore that, it helps to take a small step back and remember something important about the universe. Most of it is already invisible. When astronomers map galaxies, they're tracing the luminous parts, stars, glowing gas, bright structures. But those visible components make up only a small fraction of the total matter in the universe. The rest is something we call dark matter. We can't see it directly. It doesn't emit light. But we know it's there because of the way gravity behaves. Galaxies rotate faster than they should if only visible matter were present. Clusters of galaxies hold together more strongly than expected. Light bends as it passes through regions where no visible mass is detected. All of this points to something unseen, shaping the structure of the universe. And importantly, dark matter is not evenly distributed either. It forms its own kind of structure, often aligning with the cosmic web. So when we look at a region like the Bhuta's void and say it's empty, what we really mean is that it's empty of visible galaxies. But what about the dark matter? Is the void empty of that as well? The answer appears to be mostly. Even dark matter is underdense in voids. The same processes that pulled ordinary matter into filaments and clusters also affected dark matter. So the void is not just lacking in stars and galaxies, it's lacking in mass overall. But lacking doesn't mean completely absent. There is still some dark matter present, just in much lower concentrations. A faint, almost ghost-like presence, spread thinly across the region. And that leads to an interesting thought. If most of the universe is invisible to begin with, and the Bhuta's void is a region where even that invisible matter is sparse, then what we're dealing with is not just emptiness, but extreme emptiness. A kind of thinning of reality, where both visible and invisible components are reduced. Now, let's consider another possibility. Gas. Even in regions without galaxies, there can still be intergalactic gas. Hydrogen, mostly, spread out in very low densities. In denser regions, this gas can cool, collapse, and form stars. But in a void, the density is so low that this process becomes inefficient. The gas remains diffuse, too thin to easily form new structures. Still present, but quiet. Not glowing brightly, not forming stars, just drifting. And because it's so diffuse, it's very difficult to detect. It doesn't emit much light. It doesn't stand out. So in a sense, part of what's hiding in the void is simply matter that is too spread out to notice easily. Now there's also the question of whether there could be unknown structures, things we haven't yet identified or fully understood. This is where the conversation becomes a little more speculative, but still grounded in science. For example, there are ideas about very faint galaxies. Galaxies with so few stars or so little brightness that they're difficult to detect even with powerful telescopes. Could some of these exist within the boat's void? Possibly. If they do, they would be extremely faint, easy to miss. And because the void is so large, even a small number of such galaxies wouldn't significantly change its overall emptiness. They would still be isolated, still separated by enormous distances. So even if something is hiding there in that sense, it wouldn't transform the void into a dense region. It would remain, fundamentally, a place of low density. Now, there's another layer to this idea, not about what is physically present, but about what we might expect to find based on our models. In cosmology, we simulate the evolution of the universe using known physics. We start with initial conditions, small fluctuations in density, and then let gravity shape the structure over time. These simulations produce cosmic webs, filaments, clusters, and voids, and generally, they match what we observe quite well. But when we look at extreme cases like the Bhuta's void, we can ask whether our models fully capture what's happening. Is the void exactly what we expect from those simulations, or is it slightly more extreme than predicted? So far, it seems that while the Bhuta's void is unusual, it doesn't require new physics to explain. It can be understood as a rare but possible outcome of the same processes that shape the rest of the universe, which is in a way reassuring. It means that the void isn't hiding some entirely unknown phenomenon. It's part of the same story, just told in a quieter way. Now, let's return to the idea of hiding from a different angle. Not in terms of matter, but in terms of perception. When we look at the night sky, we see what our instruments allow us to see, and those instruments have limits. There are things too faint, too distant, or too diffuse to detect easily. So when we say a region is empty, we're also saying that it's empty to the best of our current observations. That leaves room, always, for refinement, for discovering more subtle features, for improving our understanding. But even with that in mind, the overall picture of the Bhuta's void remains consistent. It is a region of extremely low density, a place where both visible and invisible matter are sparse, a place where galaxies are rare. Now here's a gentle way to think about it. Imagine walking through a landscape at night. You have a small light with you. It illuminates what's nearby, but beyond that, the darkness hides details. You might think the landscape is empty, but in reality there could be subtle features just beyond your light's reach. Now increase the scale of that idea to cosmic proportions. Our telescopes are powerful, but they still have limits. There may be faint structures within the void that we haven't fully mapped. But even so, the overall emptiness remains. The large-scale absence of galaxies is clear, and that absence is what defines the void. So while it's natural to wonder whether something might be hiding there, the answer is, in a way, both yes and no. Yes in the sense that there is still matter, dark matter, gas, faint structures that are not immediately visible. No in the sense that nothing hidden there changes the fundamental nature of the void. It remains one of the most underdense regions we know, a place where the universe's usual abundance becomes scarcity. And that brings us gently to the next question. If the void is not hiding something fundamentally different, then how did it come to be this way in the first place? What processes led to such an extreme region of emptiness? Long before the boat's void became the vast, quiet region we observe today, it was just another part of a much younger universe. Not empty, not structured, not yet defined in any clear way. Just a slightly uneven distribution of matter, spread across space in ways so subtle that, at first, they might have seemed almost insignificant. And that's where the story begins. Because the formation of something as enormous and underdense as the Bhuta's void doesn't require a dramatic event. No explosion, no sudden clearing, no cosmic force sweeping matter away. Instead, it emerges from something much quieter. Tiny differences. Now, let's slow that idea down. In the early universe, shortly after the Big Bang, matter was distributed almost evenly. Not perfectly, but very close. There were small fluctuations, regions where the density was slightly higher or lower than average. These differences were incredibly small, so small that, if you could have observed them directly at the time, they might not have stood out at all. But gravity has a way of amplifying even the smallest imbalances. Regions with slightly more matter exerted a slightly stronger gravitational pull. They began to attract more material from their surroundings. As they gathered more matter, their pull increased. A feedback loop, slow, steady, and persistent. At the same time, regions with slightly less matter experienced the opposite effect. They had less gravitational pull, so instead of gathering material, they gradually lost it to neighbouring regions. Matter flowed outward. Not all at once, not in any dramatic way, but gradually over immense spans of time. This process, repeated across the entire universe, gave rise to the cosmic web. Dense regions became filaments and clusters, underdense regions became voids, and the Boötes void is thought to be one of the most extreme outcomes of that process. But that's only the starting point, because while this general mechanism explains the formation of voids, it doesn't fully explain why some voids become so much larger and emptier than others. So scientists have developed a few ideas to explore that question. One of the simplest explanations is statistical. In a universe as large as ours, even rare configurations are expected to occur somewhere. If you imagine the early density fluctuations as a kind of cosmic landscape, with tiny hills and valleys, then most regions would evolve into moderate structures. But occasionally, you might have a deeper valley, a region where the initial density was slightly lower than average. Over time, that small difference would be amplified. Matter would flow away more efficiently. The region would become emptier than its surroundings, and as that process continued, it could grow into something like the Boötes void. In this view, the void is not fundamentally different from other voids. It's just an extreme example, a rare but natural outcome of the same processes that shape the rest of the universe. Now there's another idea that builds on this. Instead of a single underdense region growing over time, the Boötes void might have formed through the merging of smaller voids. In the early universe, many small underdense regions would have existed. As matter flowed away from them, they would expand, and as they expanded, some of them would begin to overlap. When two voids meet, they don't remain separate. They merge, creating a larger void. Over billions of years, this process can repeat. Small voids combine into larger ones combine into even larger ones, until, eventually, you end up with a region as vast as the Boötes void. This idea fits well with what we observe in simulations of the universe. Void merging is a natural part of cosmic evolution, and it provides a way to build up large voids from smaller beginnings. Now, let's consider another possibility: the influence of the surrounding structure. The Boötes void is not isolated. It is surrounded by filaments and clusters, regions where matter has gathered more densely. If those surrounding regions are particularly massive or well-formed, they can exert a stronger gravitational pull, drawing matter away from the void more efficiently. In that scenario, the void becomes emptier not just because of its initial conditions, but because of what's happening around it. The surrounding structures act like gravitational sinks, pulling material outward, leaving the void behind. This creates a kind of contrast. Dense regions become denser, underdense regions become emptier, and the boundaries between them become more pronounced. Now, there's also the role of dark matter. Even though we can't see it directly, dark matter plays a crucial part in shaping the universe. It forms the underlying framework upon which galaxies and structures build. If the distribution of dark matter in the region that became the Boötes void was particularly low to begin with, that could have influenced how the void evolved. Less dark matter means less gravitational pull. Less pull means less matter gathering. And over time, that leads to a more pronounced underdensity. So in that sense, the void's origin may be tied not just to visible matter, but to the invisible structure beneath it. Now, it's worth noting that none of these explanations are mutually exclusive. They can all contribute. The Botha's void may be the result of slightly lower initial density, combined with the merging of smaller voids, combined with strong gravitational influence from surrounding structures. A combination of factors, all working over billions of years, and that's often how cosmic structures form, not from a single cause but from the interplay of many. Now, here's something interesting. Despite the scale and extremity of the Botha's void, it doesn't require any exotic or unknown physics to explain. It fits within our current understanding of cosmology. The same equations, the same principles that describe galaxy formation and cosmic structure can account for its existence. It's just a case where those principles have produced an unusually large and empty region. And that's an important point, because it means that the void is not an anomaly in the sense of being unexplained. It's an extreme but understandable part of the universe. Now let's think about the timescale of this process. The formation of the Botha's void didn't happen quickly. It unfolded over billions of years, gradually, imperceptibly on human timescales, matter flowing outward, structures forming around it, the void expanding, becoming more pronounced, and even today that process continues. Voids don't stop evolving. As the universe expands, and as matter continues to move under the influence of gravity, voids can grow larger. Their densities can decrease further. The contrast between voids and filaments can become sharper. So the Botha's void we observe now is not a finished structure. It's a moment in an ongoing process, a snapshot of how the universe looks at this stage of its evolution. Now, there's one more subtle idea worth considering. When we look at something like the Botha's void, it's tempting to think of it as a place, a region with boundaries, a defined structure. But in reality, it's better thought of as a pattern in the distribution of matter, defined not by solid edges but by gradual changes in density, which means that its formation is not about something being carved out or removed. It's about how matter flows and organizes itself over time, a kind of natural shaping process. Now, if you imagine that process continuing into the future, something interesting emerges. The void may become even emptier. The surrounding structures may become more pronounced. The contrast may increase. In a very slow, very gradual way, the universe may become more structured, more differentiated between dense regions and empty ones. Long after the early universe settled into its first patterns, something subtle but far-reaching continued to unfold. Not something you would notice in a single moment. Not something that changes your surroundings in any immediate way, but something that quietly stretches everything, everywhere. The expansion of the universe. And when you place the Botha's void within that larger context, its emptiness begins to take on an even deeper meaning. Because the void is not just empty, it is becoming emptier. To understand that, it helps to start with a simple idea. Space itself is expanding. Galaxies are not just moving through space, the space between them is increasing. Over time, distant galaxies drift farther apart. Not because they're actively travelling away like objects thrown into the air, but because the fabric of the universe is stretching. Now, in regions where matter is dense, like clusters of galaxies, gravity can counteract that expansion. Galaxies remain bound together. They orbit, interact, merge. Their local environment stays relatively stable, but in regions where matter is sparse, like voids, there is much less gravity to resist the expansion, and so the expansion becomes more noticeable. The distances between objects increase more freely. The space grows. Now imagine that happening inside a void. You already have a region where galaxies are far apart, where matter density is low, where gravitational pull is weak compared to surrounding structures. As the universe expands, those distances increase. The few galaxies that exist inside the void drift farther from one another. The void itself grows, not because something is pushing it outward from within, but because the space inside it is stretching, and because there is so little matter to hold things together, that stretching happens more easily. Now, let's slow that idea down and sit with it. Imagine you're looking at a large open area. Over time, that area slowly expands. The objects within it move farther apart. If there are only a few objects to begin with, the space between them becomes even more pronounced. Eventually, the distances become so large that each object feels almost completely isolated. That's what's happening in the Buddha's void. And not just now, but continuously, over billions of years. Now there's another layer to this. The expansion of the universe is not just continuing, it's accelerating. Observations of distant galaxies have shown that the rate of expansion is increasing over time. This acceleration is attributed to something we call dark energy. We don't fully understand what dark energy is, but we can observe its effects. It causes distant galaxies to move away from us faster and faster, and it influences how structures in the universe evolve. In dense regions, gravity still dominates on local scales. But on larger scales, especially in low-density regions like voids, the influence of dark energy becomes more significant. It enhances the expansion, it stretches space even more, which means that voids don't just grow, they grow faster than they would if the expansion were constant. Now let's bring this back to the Buddha's void. Over time, as the universe expands and dark energy continues to drive that expansion, the void will become larger. The distances between its few galaxies will increase, the density will decrease further, and the contrast between the void and the surrounding filaments will become even more pronounced. In a sense, the void is being gently pulled apart, not by any force acting directly on it, but by the overall expansion of space. And because it starts out so underdense, it responds more strongly to that expansion. Now here's something interesting to consider. If you were inside the Buddha's void, and you could observe the distant universe over an extremely long period of time, you would notice galaxies drifting away from you. Not just slowly, but increasingly quickly. The surrounding structures would recede. The visible universe would become more sparse, more distant, more difficult to observe. Over time, fewer galaxies would remain within your observable range, not because they disappeared, but because they moved beyond the limits of what light could reach you. And that leads to a subtle but profound idea. In the far future, regions like the Buddha's void could become even more isolated, not just in terms of distance, but in terms of observable reality. The universe, from that perspective, would appear emptier than it does today. Now, let's think about what this means for the overall structure of the universe. As time goes on, the cosmic web becomes more pronounced. Dense regions remain bound. Voids expand. The contrast increases. It's a bit like a pattern becoming clearer over time. The lines sharpen, the gaps widen, and the overall structure becomes more defined. But that definition comes with increasing separation. The universe becomes more structured, but also more divided. Clusters of galaxies remain together, but the distances between clusters grow, and voids like the Buddha's void become larger, more dominant features of the cosmic landscape. Now, here's a gentle way to picture this. Imagine a network of islands connected by bridges. Over time, the bridges stretch. Some eventually become too long to cross. The islands remain, but the connections between them weaken. Eventually, each island feels more isolated, not because it has changed, but because the space between them has grown. The Buddha's void is like one of the largest stretches of ocean between those islands, and as the universe expands, that ocean becomes even wider. Now, it's important to remember that all of this happens on timescales far beyond human experience, billions of years, trillions even, if we look far enough into the future. So from our perspective, the void appears relatively stable. Its size and structure don't change in any noticeable way over a human lifetime, but on cosmic timescales, it is evolving, slowly, steadily, becoming more empty. Now, there's something quietly fascinating about that, because it suggests that emptiness is not just a static feature. It's something that can grow, something that can become more pronounced over time. And in a universe where most of the volume is already made up of voids, that trend has interesting implications. It means that, in a very long-term sense, emptiness may become an even more dominant aspect of the universe, not because matter disappears, but because it becomes more separated, more distant, more isolated. Now, as we continue, we'll shift perspective slightly again, from the large-scale evolution of the universe back to a more familiar idea. What would it mean if our own galaxy, or even our own planet, were located inside a region like the Bhuta's Void? How would that change what we see, what we understand? Picture something slightly different this time, not drifting through the Bhuta's Void as a traveller, not observing it from afar, but beginning from a place that feels familiar, Earth. The same sky, the same ground beneath you, the same quiet moment of looking upward at night, except, without changing anything about Earth itself, you change where it exists in the universe. Instead of being part of a galaxy embedded within the denser regions of the cosmic web, you place our entire galaxy, the Milky Way, deep inside the Bhuta's Void. At first, nothing nearby would seem different. The sun would still shine, the planets would still orbit, the stars within our galaxy would still fill the night sky, constellations would still form, the Milky Way would still stretch across the darkness as a faint band of light. From a local perspective, life would feel almost identical, but the moment you look beyond our galaxy, the differences would begin to emerge, slowly at first, then unmistakably. In our current location, we are part of a relatively populated region of the universe. Nearby galaxies like Andromeda are close enough to observe clearly with telescopes. Clusters and filaments form a larger structure that, while not visible to the naked eye, becomes apparent through observation. There is a sense, even if subtle, that we are part of something interconnected. Inside the Bhuta's Void, that connection would feel much weaker, because the nearest galaxies would be much farther away. Not just a little farther, but separated by tens or even hundreds of millions of light years. That changes the sky in a very specific way. If you are standing on Earth and looking outward with even powerful telescopes, the number of visible galaxies would drop dramatically. The deep sky would appear quieter. Instead of a rich field of distant galaxies, you would see fewer points of light, more darkness between them. The universe would feel more sparse. Now, this has an interesting consequence. Our understanding of the universe is shaped by what we can observe. We build models based on patterns, distributions, and relationships. If we were inside the Bhuta's Void, those observations would be different. We might conclude that galaxies are more isolated than they actually are, that the universe contains fewer large-scale structures, that the cosmic web is less pronounced, or perhaps not even apparent at all. In other words, our picture of the universe would be incomplete, not because we lack intelligence or curiosity, but because our environment would limit what we can see. And that's a subtle but important idea. Knowledge is shaped by perspective. Now let's consider another effect: distance. If the nearest galaxies are much farther away, then studying them becomes more difficult. Even with advanced technology, the light from those galaxies would be fainter, harder to resolve, harder to analyze in detail. Certain discoveries might take longer. Some might be delayed significantly. For example, understanding that galaxies exist beyond our own might require more sensitive instruments. Recognizing large-scale structure might take longer to piece together. Even measuring the expansion of the universe could be more challenging, depending on what objects are available to observe. Now, that doesn't mean it would be impossible. Given enough time and technological advancement, many of the same discoveries would still be made. But the path to those discoveries might look different. Slower in some ways, less direct. Now let's think about the night sky itself. To the naked eye, most of the stars we see belong to our own galaxy, so that part of the sky wouldn't change much. But if you were to look for faint distant galaxies, the kind that appear as small smudges of light in telescopes, you would find fewer of them. The sky beyond the Milky Way would feel emptier, less populated, more distant, and over time, as the universe continues to expand, that effect would become even more pronounced. Distant galaxies would drift farther away. Their light would become redshifted, stretched to longer wavelengths. Eventually, some might move beyond the range of what we can detect at all. From within the void, the observable universe could become increasingly sparse. Now there's another interesting implication: cosmic isolation. In our current location, our galaxy is part of a group. We have neighbours. We interact gravitationally. Over time, galaxies in our local group are expected to merge. There is a sense of future interaction. Inside the Bhuta's void, that future might look different. If the Milky Way were isolated enough, it might not have nearby galaxies to merge with. Its long-term evolution could be more solitary, less influenced by external interactions, more driven by internal processes. In that sense, our galaxy would become one of those lonely galaxies we talked about earlier. Now, let's bring this back to something more reflective. Imagine growing up in such a universe, looking at the night sky, studying it, trying to understand its structure. You might develop a sense that the universe is vast, quiet, and sparsely populated. You might not immediately realize that elsewhere there are regions filled with dense clusters of galaxies, because those regions would be far beyond your immediate observational reach, and that changes something subtle. It changes your expectations. You might think that what you see locally is representative of the whole, that the universe is mostly empty, with occasional isolated galaxies, which, in terms of volume, isn't entirely wrong. But it misses the richness of the cosmic web. Now here's something quietly fascinating. From our actual position in the universe, we're not in the densest region, but we're not in a deep void either. We occupy a kind of middle ground, dense enough to observe nearby galaxies, sparse enough to see large-scale structure. That position gives us a relatively balanced view. But if we were deep inside the Bhuta's void, that balance would shift. Our window into the universe would narrow. And that reminds us of something important. Our understanding of the cosmos is always tied to where we are within it. Now, let's imagine one more aspect. Communication. If there were other civilizations in distant galaxies, the distances inside the void would make any form of communication extraordinarily slow. Signals would take hundreds of millions of years to travel, which means that, in any practical sense, interaction would be impossible. Each galaxy would exist in near complete isolation, a collection of separate worlds, each unaware of the others in any immediate way, and that deepens the sense of separation, not just physical, but informational. Now, as you sit with this idea, something interesting happens. The void stops being just a distant, abstract region. It becomes a possible environment, a different way the universe could have looked from our perspective, and that shift makes it easier to understand just how much our own location shapes what we know. Because if Earth were inside the Bhuta's void, the universe we describe today might have taken much longer to discover, and even then, it might have felt very different. Compared to the distances we've been exploring, human life unfolds on a scale so small that it almost slips past unnoticed. Not in importance, of course, but in sheer size and duration. And when you place something like the Bhuta's void alongside the span of a single human life, the contrast becomes quietly difficult to hold on to, because we are used to measuring things in years, decades maybe. A long life might stretch to 80 or 90 years. A historical event might feel distant at a few hundred years. Even 1,000 years begins to feel abstract. But here, we're talking about distances that take hundreds of millions of years for light to cross. So instead of starting with the void, let's start with something closer, Imagine a single second, a brief moment, barely enough time to notice passing. Now stack those seconds together. 60 of them make a minute. 60 minutes make an hour. 24 hours make a day. Days become years. Years become decades. And eventually, you arrive at the length of a human life. Already, that's a long chain of moments. Something that feels substantial, but now continues stacking, not for a few more years, not for a few more centuries, but for millions of years, then hundreds of millions. At that point, the number of seconds becomes so large that it stops feeling like a sequence and starts feeling like an idea, and that's the kind of duration it takes for light to cross the Bootes void. Now here's where it becomes more tangible. If a beam of light began its journey across the void at the moment the first dinosaurs appeared on Earth, it still wouldn't have finished crossing by the time they disappeared. In fact, it would still be travelling long after entirely new forms of life had evolved, and that's just one crossing. Now place a human life within that timeline. A single lifetime becomes a tiny fraction, so small that if you tried to mark it along that journey, it would be almost invisible, not because it doesn't matter, but because the scale is so vast. Now, let's shift from time to space. Imagine walking across a room. A few steps and you reach the other side. Even a long journey on Earth, across continents, still feels manageable. Thousands of kilometers can be traveled within days or hours, depending on how you move. Now imagine traveling across the distance between galaxies inside the void. Millions of light years. Even at the speed of light, it takes millions of years. At any speed we can realistically achieve, the journey becomes effectively impossible. So the comparison isn't just large, it's beyond practical experience. Now here's something subtle. When we think about large numbers, we often try to relate them to something familiar. We scale them down, or we imagine them as extended versions of what we know. But at a certain point, that approach stops working. The Bootes void is one of those points. It's not just a bigger version of something we understand. It's something that requires a different way of thinking. Now let's bring this back to human life in a more reflective way. A human life is filled with events, moments that feel important, days that pass quickly or slowly depending on what happens. We measure time through experience, through change, through memory. In the void, as we've discussed, those markers are sparse, distances are vast, events are rare. Time feels stretched, not because it is, but because there is less to divide it. So when you compare the two, something interesting emerges. Human life is dense, filled with activity, interaction, change. The Bootes void is sparse, defined by distance, separation, and long intervals between events. And that contrast highlights something about perspective. What feels long to us, a quiet afternoon, a long year, is incredibly brief on cosmic scales. And what feels vast in the universe, hundreds of millions of years, is beyond direct experience. Now there's another layer to this: connection. In human life, connection happens quickly. You speak and someone hears you. You send a message and it arrives almost instantly. Even across the globe, communication is nearly immediate. Inside the void, connection is different. If you imagine trying to communicate across those distances, the delay becomes immense. A signal sent from one galaxy to another might take longer than the entire history of human civilization, which means that, in any meaningful sense, each region exists independently. That independence is part of what gives the void its character. Now, let's consider something a bit more grounded. Our entire recorded history, everything from the earliest civilizations to the present day, spans only a few thousand years. Compared to the time it takes light to cross the void, that history is almost negligible. If you placed it on that timeline, it would occupy a tiny fraction, so small that it would be difficult to distinguish. And yet, within that small span, so much happens. Cultures rise and fall, technologies develop, ideas evolve. From our perspective, it feels immense. From a cosmic perspective, it's a brief moment. Now, this contrast can feel overwhelming if you approach it directly, but there's another way to look at it, not as something that diminishes human experience, but as something that places it within a larger context. The universe operates on many scales at once: the scale of human life, the scale of planetary systems, the scale of galaxies, and the scale of structures like the Buddha's void. Each scale has its own rhythms, its own patterns. None of them cancel out the others, they simply exist together. Now, imagine standing somewhere quiet, looking up at the night sky. Even without thinking about galaxies or voids, there's already a sense of distance. The stars are far away. The sky feels deep. Now extend that feeling, not just to the nearest stars, but to the nearest galaxies, then to the distances between galaxies inside a void. The depth increases, the scale expands, and eventually you reach a point where the idea of distance becomes more about concept than measurement. Now here's something that gently ties this together. The Buddha's void is vast, empty, and defined by long time scales. Human life is small, active, and defined by short time scales. But both exist within the same universe, the same set of physical laws, the same underlying structure. Which means that, in a very real sense, the smallest moments of human experience and the largest structures in the cosmos are part of the same story. Different in scale, but connected in origin. And that connection is what allows us to think about something like the Buddha's void at all, to imagine it, to describe it, to place it alongside our own lives and reflect on the difference. If you follow the story of the universe forward instead of backward, something begins to stand out. Not immediately, not in a dramatic way, but gradually, almost quietly. The gaps get larger, the distances stretch, and regions like the Buddha's void begin to feel less like exceptions and more like a preview. Because when we ask whether voids are the universe's future, we're really asking something deeper. What happens when expansion continues for billions, then trillions of years? And what kind of universe does that create? To begin answering that, let's return to something we've already touched on. The universe is expanding, not just steadily, but at an accelerating rate. Driven by what we call dark energy, this expansion causes distant galaxies to move away from one another faster and faster over time. Now, in the present era, gravity still plays a strong role in certain regions. Galaxies that are close together remain bound. Clusters hold together. Local groups interact and merge. There is still structure, still motion, still connection. But on larger scales, especially between those structures, expansion dominates. And that's where the idea of voids becomes particularly important. Because voids are already regions where gravity is weak compared to the expansion. There's not enough mass to hold things together tightly. So the expansion of space stretches those regions more freely. Now imagine that process continuing, not for a few billion years, but for tens or hundreds of billions. Over time, galaxies that are not gravitationally bound drift farther apart. The cosmic web, as we see it today, begins to thin out. Filaments stretch, clusters become more isolated, and voids expand. They grow larger, not by actively pushing outward, but because everything else is moving away. The distances between structures increase, and the empty regions between them widen. Now, here's something subtle but important. Structures that are gravitationally bound will remain intact. A local group of galaxies, for example, is expected to stay together. Over time, the Milky Way and Andromeda will merge, forming a larger galaxy. That system will continue to exist as a single, bound structure. But beyond that local region, other galaxies will recede. Eventually, they will move so far away that their light can no longer reach us. They will pass beyond what's called the cosmic horizon, not disappearing in a physical sense, but becoming unobservable. And from any given point in the universe, something similar happens. Each region becomes more isolated over time. Now, let's bring this back to the idea of voids. As expansion continues, the universe becomes more dominated by these large empty regions. Not because matter vanishes, but because it becomes more concentrated in smaller, isolated pockets. Between those pockets, the space grows, voids expand, and in that sense, the universe becomes more void-like overall. Now imagine looking at the universe far in the future. Not from our current perspective, but from a point billions or trillions of years ahead. If you were inside a galaxy at that time, your observable universe might look very different. You might see only your own galaxy, or perhaps a small group of nearby ones. Everything else would be too far away, too distant for light to reach you. The sky beyond your galaxy would appear almost completely empty. Not because the universe is empty, but because the expansion has stretched everything beyond your observational reach. In that sense, the universe would feel like a void, even though on larger scales structure still exists. Now here's an interesting way to think about it. Today we can observe the cosmic web. We can map galaxies across vast distances. We can see clusters, filaments, and voids. We have access to a relatively rich picture of the universe. But that's because we are living at a particular time. A time when the universe is old enough to have structure, but not so old that expansion has erased our ability to observe it. In the far future, that window may close. Observers might not be able to detect the larger structure at all. They might conclude that the universe consists only of their local region, a single galaxy surrounded by emptiness, which in a way is exactly what a void feels like. Now, does that mean the entire universe will become one giant void? Not exactly, because the underlying structure, clusters and filaments will still exist. They will still contain matter, stars, galaxies, but they will be so far apart from one another that, from any given location, the universe will appear mostly empty. So the answer is a bit nuanced. Voids will not replace everything, but they will become more dominant in terms of how the universe is experienced. The empty regions will grow, the connections between structures will weaken, and isolation will increase. Now let's return briefly to the Buddha's void. In many ways, it represents an early version of this future state, a region where the effects of low density and expansion are already pronounced, a place where galaxies are sparse, distances are vast, and interactions are rare. It's not the future of the entire universe, but it offers a glimpse of what increasing separation looks like. Now, there's something quietly reflective about this idea. The universe begins in a hot, dense state. Matter is close together. Everything is connected. Over time, structure forms, galaxies, clusters, filaments, and alongside that structure, voids emerge. As time goes on, the structure becomes more defined, but also more separated, and eventually the separation becomes the dominant feature. Not because the universe is losing matter, but because it is stretching. Now, here's a gentle way to hold on to that thought. Imagine a pattern drawn on a flexible surface. At first, the pattern is compact. The lines are close together. But as the surface stretches, the pattern expands. The lines move apart. The spaces between them grow. The pattern is still there, but it becomes more spread out. That's what's happening to the universe. And in that stretching, voids play a larger and larger role. Somewhere along the way, the idea of emptiness begins to change. At first, it might have felt like a gap, a missing piece, a place where something should have been but isn't. But after spending time with it, after slowly tracing the scale, the structure, the quiet distances of the Buddha's void, that emptiness starts to feel different. Not incomplete, just part of the whole. Because everything we've explored, the size, the absence of galaxies, the slow passage of light, the isolation, the expansion, it all points to something simple. The universe is not filled evenly. It never was. It organizes itself into patterns, dense regions where matter gathers, and vast regions where it does not. Both shaped by the same forces, both equally real. Now, instead of trying to measure it again, Instead of adding more numbers or comparisons, let's just sit with the idea for a moment. A region hundreds of millions of light years across, so large that light itself takes longer than the rise and fall of entire species to cross it, so empty that galaxies become rare, distant, almost incidental, and yet still part of the same structure that includes everything we know. It's not separate, not outside, just quieter. And that quiet has a certain quality to it. Not silence in the way we think of it on Earth, where sound simply isn't present, but a kind of stillness in structure, fewer interactions, fewer interruptions, long stretches where nothing much changes, and in that stillness something becomes easier to notice, scale, not as a number, but as a feeling. The sense that the universe is far larger, far less dense, far more spread out than our everyday experience suggests. Now, bring that back gently to where you are, wherever you happen to be listening from, a room, perhaps, or somewhere quiet. You're surrounded by things that are close, walls, objects, sounds, everything within reach. And yet, beyond that immediate space, there is a planet. Beyond that, a solar system. Beyond that, a galaxy. And beyond that, a network of galaxies stretching across the universe. And somewhere within that network, regions like the Butter's Void exist, not as distant abstractions, but as real parts of the same universe you're in. Now, there's something quietly reassuring about that, because even though the scales are so different, the same physical laws apply, the same gravity, the same light, the same passage of time. What changes is not the rules, but the arrangement. And in some places that arrangement leads to complexity. Crowded regions, interactions, constant change. In other places it leads to simplicity, space, distance, stillness. Neither is more correct than the other. They are just different expressions of the same underlying reality. Now, if you let your thoughts drift for a moment, you might imagine that vast empty region again. Not in detail, not trying to picture every distance, but just the idea of it. A place where galaxies are few, where light travels uninterrupted for immense stretches, where time feels less divided by events. And instead of trying to understand it all at once, you can simply let it exist. A quiet part of the universe. Now, there's a subtle shift that can happen here. At the beginning, something like the Butter's Void might feel overwhelming. Too large, too empty, too distant from anything familiar. But by now, it might feel a little more approachable. Not because it's become smaller, but because it's been placed into context, connected to the same processes, the same structure, the same universe that includes everything else. And that connection matters, because it means that even the emptiest regions are not separate from the story. They are part of it. Now, as things begin to slow down, there's no need to hold on to every detail, no need to remember every number or concept. The important part is the sense of scale, the contrast between what is present and what is absent, and the understanding that both are essential to the structure of the universe. You can let the details fade a little, let the ideas settle. Imagine that vast region once more, not as something to analyse, but as something to rest your thoughts on. Open, uncrowded, still. And as you do, you might notice that there's something familiar about that kind of space. Not in a literal sense, but in the feeling of it. A kind of mental quiet. A place where there's room for thoughts to slow down. Where nothing is pressing for attention. Where time feels less divided. Now, gently, bring your awareness back to the present. To where you are, to the small immediate space around you. The contrast remains, the vast and the small, the distant and the near, both existing at the same time, and somewhere, far beyond anything you can see directly, the Butter's Void continues to exist, not changing in any noticeable way, not demanding attention, just being what it is. A reminder that the universe is not only made of things that fill space, but also of the spaces between them, And sometimes those spaces are the most revealing of all. So as the thought settles, there's nothing left to do, no conclusion to reach, just a quiet awareness of scale, and the understanding that even in the largest emptiness, there is still something there to notice.